Settle into this quiet space and let the finite concerns of the day begin to dissolve. Tonight, we journey into a realm that defies intuition, a landscape built from pure thought that stretches beyond all physical limits. We explore the concept of infinity. It is not merely a large number, but a completely different mode of existence, an idea that, when examined closely, generates profound and beautiful paradoxes. These are mind-bending math concepts that challenge our understanding of size, space, motion, and even reality itself. This is your invitation to fall asleep amidst infinite ideas, to let your mind float in the unfathomable. Do not try to solve these puzzles. Simply witness them, contemplate them, and allow their strange logic to guide you into a state of deep relaxation. Our journey into the infinite begins now. Hilbert's infinite hotel paradox. Imagine a grand hotel, a structure of impossible architecture stretching endlessly into the horizon. This is Hilbert's infinite hotel, a famous thought experiment conceived by mathematician David Hilbert. It has an infinite number of rooms, each numbered sequentially, room 1, room 2, room 3, and so on forever. Now, imagine that on this particular night, the hotel is completely full. Every single one of the infinite rooms is occupied by a guest. There are no vacancies. From our experience with the finite world, this seems straightforward. A full hotel cannot accept new guests. But this is where our intuition first encounters the strange hospitality of infinity. The paradox begins when a new guest arrives at the reception desk, seeking a room for the night. Can the hotel accommodate them? The answer, paradoxically, is yes. This is how the logic of infinity begins to bend our minds. The hotel's manager, well-versed in transfinite arithmetic, simply makes an announcement to all the currently occupied rooms. Each guest is politely asked to move from their current room, room N, to the next room, room N+1. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 1,000,000 moves to room 1,000,001. Because there is no last room in an infinite hotel, every guest has a new room to move into. This coordinated shift creates a cascade down the infinite corridor of rooms, and in doing so, it leaves one room empty, room 1. The new guest can now check in. The hotel, once completely full, has effortlessly made space for one more. This first step reveals a fundamental property of countable infinity. Infinity plus 1 is still just infinity. The size of the set has not changed. But the paradox deepens, revealing the truly mind-bending nature of this concept. Now, imagine a new situation. An infinitely long bus arrives, carrying an infinite number of new guests, each seeking a room. The hotel is, again, completely full. Surely, our finite intuition tells us, it is impossible to accommodate an infinite number of new guests in a hotel that is already infinitely full. Yet, once again, the manager has a solution. This time, the announcement asks every current guest to move from their current room, room N, to a new room, room 2N. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6, and so on. This action places all the original guests into the set of all even-numbered rooms. And what does this leave empty? All of the odd-numbered rooms. Room 1, room 3, room 5, room 7, and so on. An infinite number of empty rooms has just been created, ready for the infinite number of new guests from the bus. This astonishing result demonstrates another property of countable infinity. Infinity multiplied by 2 is still the same size of infinity. The set of all integers and the set of all even integers have the same cardinality, the same number of elements, even though one is a proper subset of the other. This is one of the defining characteristics that separates the infinite from the finite. In a finite hotel, if half the rooms are occupied, it's half full. In Hilbert's infinite hotel, if all the even-numbered rooms are occupied, the hotel is still, in a sense, just as full and just as empty as it was before, capable of holding yet more infinities. We could even imagine an infinite number of buses arriving, each with an infinite number of guests, and through clever assignments using prime numbers, the hotel could accommodate them all. Hilbert's infinite hotel paradox is not a true logical contradiction, but rather a veridical paradox. A situation that seems absurd but is demonstrably true within a formal logical system. It serves as a powerful pedagogical tool to illustrate the profoundly counterintuitive properties of infinite sets as explored by George Cantor. It forces us to abandon our ingrained, finite world intuitions about concepts like full, size, and number. It teaches us that infinity is not just a very large number you can never reach. It is a different kind of quantity altogether, governed by its own strange and beautiful rules, the rules of transfinite arithmetic. The paradox questions our intuitive understanding of space and quantity. It suggests that if physical space were truly infinitely divisible or extensive in certain ways, it might harbor these same bizarre properties. It challenges us to accept that logic can lead us to truths that our senses and everyday experience cannot easily accommodate. The hotel becomes a metaphor for the mind's capacity to conceive of realities far beyond the tangible world. As you continue to fall asleep, let the image of Hilbert's infinite hotel expand in your mind's eye. See the endless corridor of doors. Feel the strangeness of a full hotel that always has more room. Contemplate the idea that infinity can be manipulated, folded, and rearranged in ways that defy common sense. Let go of your finite understanding of space and number. Find deep relaxation in the sheer vastness of this concept. Appreciate the paradox not as a problem, but as a gateway to a larger, stranger, and more wondrous mathematical universe, resting peacefully in a conceptual space that has no limits. Zeno's Paradoxes. Let us now journey back in time to ancient Greece, to confront a series of brilliant paradoxes that challenge the very possibility of motion. Devised by the philosopher Zeno of Elea, these puzzles use the concept of infinity to create seemingly inescapable logical contradictions, questioning whether movement through space and time, an experience fundamental to our existence, is actually coherent or perhaps just an illusion of our senses. While our experience tells us that we move constantly and effortlessly, Zeno's paradoxes present powerful arguments suggesting that motion, when analyzed logically, might be impossible. This profound clash between reason and experience is a deep mind fuck, inviting contemplation on the nature of space, time, and the infinite divisions within them as you relax into stillness. First, consider the dichotomy paradox. To travel any distance, you must first cover half of that distance. To cover the remaining half, you must first cover half of that distance, a quarter of the total. And before that, half of the quarter, an eighth, and so on forever. The journey is thus broken down into an infinite number of sequential tasks. Zeno's challenge is this: how can you complete an infinite number of tasks in a finite amount of time? Before you can even take the first step, you must complete the infinite process of traversing the halfway points to that first step. Logically, it seems motion can never even begin. The infinite divisibility of space appears to create an endless, insurmountable series of prerequisites for any movement at all. Then, consider the more famous paradox of Achilles and the tortoise. The swift-footed hero Achilles is set to race a slow tortoise, to whom he gives a generous head start. To win, Achilles must first reach the tortoise's starting point. In the time it takes him to do that, the tortoise will have crawled a short distance ahead to a new point. Now Achilles must reach this new point. But again, in the time that takes, the tortoise will have moved a little further still. This continues ad infinitum. Achilles must cover an infinite number of ever-decreasing distances to catch up to the tortoise, and during each of these intervals, the tortoise makes its own small advance. Logically, it seems Achilles can get infinitely close to the tortoise but never actually overtake it. The tortoise will always be a tiny yet real distance ahead. Finally, consider Zeno's arrow paradox. At any single frozen instant of time, an arrow in flight is not moving. It occupies a specific portion of space exactly equal to its own length. If at any given instant it is not moving, and time is composed of a series of such instants, how can the arrow ever be said to be in motion? If at every now, it is at rest, where does the movement come from? It's like a film composed of perfectly still frames. This paradox questions how a sequence of static moments can combine to create the dynamic experience of motion. These paradoxes, while seemingly different, all exploit the same core concepts: the infinite divisibility of space and time, and the difficulty of summing an infinite series. For centuries, they posed a genuine challenge to philosophers and mathematicians. The modern mathematical resolution comes primarily from the development of calculus and the understanding of convergent infinite series. We now know that an infinite number of terms can add up to a finite sum. In the dichotomy and Achilles paradoxes, the successively smaller distances and time intervals form a convergent series. While Achilles must complete an infinite number of tasks, the time required to complete each task also decreases infinitely, and the sum of all these time intervals converges to a specific finite moment when he does, in fact, overtake the tortoise. Mathematics provides a consistent language to describe how an infinite number of points can be traversed in finite time. However, does the mathematical solution fully dissolve the philosophical mystery? Many argue it does not. The paradox still forces us to confront the bizarre nature of continuous space and time. If space is truly continuous like the real number line, then any finite distance does contain an infinite number of points. How does a physical object actually traverse these points? Does it perform an infinite number of mini-tasks in a kind of supertask, a concept we might explore later? Or does the paradox hint that our conceptual model of space and time as continuous, infinitely divisible continuum might be flawed? Could reality at its most fundamental level be discrete? Perhaps there is a smallest possible unit of distance, the Planck length, and a smallest possible unit of time, the Planck time, below which the concept of division becomes meaningless. If so, space is not infinitely divisible, Zeno's infinite series never arises, and the paradoxes dissolve because there's a finite number of pixels of spacetime to cross. This remains a key question in theoretical physics. Zeno's paradoxes, therefore, remain a profound mind-bending exploration of the relationship between mathematical models and physical reality. They question whether the abstract concept of infinity can be coherently applied to the real world of motion, space, and time. They highlight the tension between our logical analysis of the world and our direct, undeniable experience of it. As you continue to fall asleep, feel the stillness of your own body, and yet be aware of the constant, subtle motions within, the rising and falling of your chest, the beating of your heart. Contemplate the paradox of movement, the journey across a room that seems to contain an infinity of halfway points. Let the logical impossibility presented by Zeno clash gently with the experienced reality of flow and change. Find deep relaxation not in solving the paradox, but in marveling at the mystery it reveals. The profound enigma of how anything moves at all in a world that can be endlessly divided, resting peacefully within the deep, continuous, yet infinitely complex flow of time and space. The Banach-Tarski Paradox. Prepare to encounter a paradox so profoundly counterintuitive, so utterly defiant of physical reality, that it has been described as a mindfuck even by seasoned mathematicians. This is the Banach-Tarski Paradox, a theorem in set theory that makes a truly astonishing claim. A solid three-dimensional sphere can be decomposed into a finite number of special, non-overlapping pieces, which can then be put back together through rotations and translations alone, no stretching or bending, to form two identical copies of the original sphere. Let that sink in. Take one golden ball, break it into a few specific sets of points, move those pieces around and reassemble them into two golden balls, each identical in size and shape to the original. This is not a physical trick. It is a mathematically proven theorem. It seems to violate our most fundamental intuitions about conservation of volume and the nature of physical objects, questioning the very relationship between abstract mathematical truth and the tangible reality of our existence. This is a journey into the strange world of non-measurable sets and the axiom of choice, an invitation to fall asleep pondering the possibility of creating something from nothing through the bizarre logic of infinity. How can such a thing be possible? The key lies in the nature of the pieces into which the sphere is decomposed. These are not the kind of pieces you could cut with a knife. They are infinitely complex, abstract collections of points, so scattered and intricate that they lack a well-defined volume in the ordinary sense. They are what mathematicians call non-measurable sets. Think of them not as solid chunks, but as infinitely fine, interpenetrating clouds of dust, so porous and bizarrely structured that our intuitive notions of size and volume simply break down. The paradox works by exploiting the infinite nature of the points within the sphere. It gathers up these infinite points and cleverly rearranges them to fill the space of two spheres. The proof of the Banach-Tarski paradox relies on a foundational, but controversial, principle in modern mathematics known as the axiom of choice. This axiom states that given any collection of non-empty sets, it is possible to choose exactly one element from each set, even if the collection itself is infinite and there is no rule or procedure for making the choice. The axiom of choice allows mathematicians to handle and make selections from infinite sets in powerful ways, but it also leads to deeply non-intuitive results like this paradox. For this reason, some mathematicians have worked in systems that reject the axiom, but it is a standard and essential tool in many areas of advanced mathematics. The paradox is, in a sense, a dramatic illustration of the strange consequences of accepting this powerful axiom when dealing with infinity. It's crucial to understand that the Banach-Tarski paradox does not violate any laws of physics. You cannot actually perform this trick with a physical object like an orange or a gold ball. Physical objects are made of a finite number of atoms, which are not infinitely divisible points. You cannot cut matter into the infinitely complex, non-measurable pieces required. The paradox exists purely in the abstract realm of mathematical geometry and set theory. It describes what is possible with the idealized, continuous, point-set sphere of mathematics, not the granular, atomic sphere of the physical world. Yet, this distinction is what makes the paradox so profoundly unsettling. It creates a vast chasm between mathematical truth and physical intuition. If mathematics is the language we use to describe reality, what does it mean when that language produces theorems that are so flagrantly at odds with physical existence? It questions the nature of mathematical objects themselves. Do these non-measurable sets exist in some Platonic realm of mathematical reality, or are they merely artifacts, pathologies generated by pushing our axioms and definitions into strange, non-physical territory? Is the paradox revealing a deep truth about the nature of space and infinity, or is it revealing a limitation or strangeness in our chosen mathematical frameworks? The mindfuck here is twofold. First, the literal claim, one sphere becoming two. It breaks our mental model of conservation. Second, the implication for knowledge and reality. It shows that our most rigorous logical systems can lead to conclusions that seem like pure magic or logical impossibilities from an intuitive standpoint. It forces us to ask what truth means in mathematics. If a theorem is logically sound and derived from accepted axioms, must we accept its conclusion as true, even if it describes something physically impossible and conceptually bizarre? It highlights the difference between mathematical space and physical space, and the potential dangers of applying intuitions from one realm to the other. This paradox is a humbling reminder of the sheer strangeness of infinity. The infinite set of points in a sphere is so vast and can be arranged in such complex ways that it can be partitioned and reassembled to fill a space twice as large. The more points needed for the second sphere were, in a sense, already hidden within the complex structure of the infinite set of points of the first sphere. As you continue your journey towards sleep, let the impossible image of the duplicating sphere float in your mind. One ball becoming two, not through magic but through the rigorous, counterintuitive logic of transfinite mathematics. Contemplate the nature of the pieces, not solid chunks but infinitely scattered dusts of points. Acknowledge the deep mystery that separates the world of mathematical abstraction from the world of physical intuition. Let the Banach-Tarski Paradox dissolve your assumptions about volume, space, and the simple act of counting. Find deep relaxation in accepting that the universe of pure thought contains wonders and impossibilities that our physical world does not, resting peacefully within the profound, logic-defying beauty of mathematical infinity. Galileo's paradox of infinity. Long before the formal development of set theory, thinkers have grappled with the puzzling nature of infinity. The brilliant Renaissance astronomer and physicist Galileo Galilei encountered a particularly elegant and foundational paradox while contemplating infinite numbers, one that laid the groundwork for our modern understanding of different sizes of infinity. The paradox arises from a simple comparison. Consider all the natural numbers, 1, 2, 3, 4, 5, and so on, an infinite set. Now, consider a subset of these numbers, the perfect squares, which are the result of squaring each natural number. 1, 4, 9, 16, 25, and so on. Intuitively, it seems there must be fewer perfect squares than natural numbers. After all, the squares are only a small selection from the natural numbers. There are many natural numbers, like 2, 3, 5, 6, 7, 8, that are not squares. Our finite intuition screams that the whole must be greater than its part. Yet, Galileo demonstrated a way in which the two sets seem to be the same size. This contradiction between our intuition about parts and wholes and the logic of one-to-one correspondence is Galileo's paradox. A beautiful mindfuck that questions our most basic assumptions about counting and size when dealing with the infinite, inviting you to fall asleep pondering how a part can be equal to the whole. Galileo's reasoning was simple yet profound. He noticed that you can create a perfect, one-to-one correspondence between every single natural number and every single perfect square. For every natural number n, there exists exactly one perfect square, n superscript 2. For the number 1 there is the square 1. For the number 2 there is the square 4. For 3 there is 9. For every number in the first list, you can pair it up perfectly with a unique number in the second list, and this pairing can continue forever without leaving any number out in either set, when viewed this way. If you can pair every member of one set with a unique member of another set, with none left over, modern mathematics says that the two sets have the same cardinality, or the same size. Here lies the paradox. By one line of reasoning, the subset argument, there are more natural numbers than perfect squares. By another line of reasoning, the one-to-one correspondence argument, they are equal in number, which is correct. Galileo himself was deeply perplexed by this. He concluded that concepts like equal, greater than, and less than simply do not apply to infinite quantities in the same way they apply to finite ones, and that we should not try to compare them. He saw it as a limitation of our understanding. It was George Cantor, over 2 centuries later, who would take Galileo's insight and turn it into a cornerstone of his revolutionary theory of infinite sets. Cantor made the concept of one-to-one correspondence the definition of what it means for two sets to be the same size. For finite sets, this aligns perfectly with our intuition. If a room has 10 chairs and 10 people, and each person sits in a chair with none left over, we know the number of chairs and people is equal. Cantor bravely applied this same logic to infinite sets. He concluded that Galileo's observation wasn't a contradiction to be dismissed, but a fundamental property of infinity. An infinite set can be put into a one-to-one correspondence with a proper subset of itself. The part can be the same size as the whole. This is one of the key definitions of what makes a set infinite. Galileo's paradox thus serves as a gateway to understanding the truly mind-bending nature of transfinite numbers. It forces us to abandon one of our most deeply ingrained logical axioms, that the whole is always greater than its part, an axiom that holds true universally for finite quantities but breaks down completely when we step into the realm of the infinite. It questions the reliability of our intuition when projected beyond its familiar finite domain. The paradox reveals that size, in the context of infinity, is not about containment or density, but about parability or cardinality. This concept has profound implications. It means the set of all even numbers is the same size as the set of all natural numbers. The set of all prime numbers is the same size as the set of all natural numbers. The set of all rational numbers, fractions, is also, perhaps surprisingly, the same size as the set of all natural numbers. All these are examples of the smallest type of infinity, countable infinity, which Cantor named Aleph null. They are infinite, yet they can all be put into a one-to-one correspondence with the counting numbers. Contemplating Galileo's paradox is an exercise in mental flexibility. It requires us to release a piece of logic that feels utterly self-evident and embrace a new, counterintuitive rule for a different kind of existence. It highlights the power of formal definition in mathematics to lead us to truths that intuition would resist. It's a mystery that Galileo identified but could not fully resolve, a door he opened through which Cantor would later lead mathematics into a new and fantastic paradise of different infinities. As you continue to fall asleep, picture 2 infinite lines of numbers stretching out before you, the natural numbers, 1, 2, 3, 4, and the perfect squares, 1, 4, 9, 16. Watch as a line connects 1 to 1, 2 to 4, 3 to 9. An endless, perfect pairing. Feel the tension between the intuition that one line is sparser and the logic that they are equally numerous. Let Galileo's paradox gently stretch your understanding of size and quantity. Find deep relaxation in accepting that the rules of the infinite are not the rules of the finite. The whole can be equal to its part. Rest peacefully within this simple yet reality-bending mathematical truth. Cantor's diagonal argument. Having opened the door with Hilbert's hotel and Galileo's paradox to the strange idea that all infinities might be the same size, countable, listable, capable of being put in a one-to-one correspondence with the counting numbers, we now arrive at a moment of profound rupture, a discovery that shattered this notion and revealed that the realm of the infinite is far vaster and more mysterious than previously imagined. This is George Cantor's diagonal argument, a beautiful, elegant, and utterly revolutionary proof demonstrating that there are, in fact, different sizes of infinity. Specifically, Cantor showed that the infinity of real numbers, which include all integers, fractions, and irrational numbers like pi or the square root of 2, is a fundamentally larger, uncountable infinity than the countable infinity of natural numbers. This conclusion was, and still is, a staggering mind fuck, revealing an entire hierarchy of infinities and questioning our very concept of infinity as a single monolithic idea. The diagonal argument is a masterpiece of logical reasoning that proves the existence of something we can never fully list or count, inviting you to fall asleep contemplating the layers within the infinite. Cantor's proof is a form of reductio ad absurdum, or proof by contradiction. It begins by assuming the opposite of what it seeks to prove. So, let's assume, for the sake of argument, that we can create a complete, exhaustive, infinite list of all the real numbers between 0 and 1. This assumption means we believe the set of these real numbers is countably infinite, just like the natural numbers. We could, in theory, list them out, the first number, the second number, the third, and so on, forever, eventually including every single real number between 0 and 1. Imagine such a list. It might look something like this, written in decimal form. The first number, 0, 141592. The second number, 0, 318281. The third number, 0, 884626. The fourth number, 0, 235399. And so on, forever, with our list supposedly containing every possible real number. Now, Cantor invites us to perform a simple, ingenious construction. We are going to create a new number, let's call it C, for Cantor, also between 0 and 1 by going down the diagonal of our supposedly complete list. We construct C using a simple rule. For each digit of C, we look at the corresponding digit on the diagonal of our list and choose a different digit. For example, if the digit on the list is a 1, we make our digit a 2. If it's anything else, we can make it a 1. Let's build our new number, C, using our example list. The first digit of the first number on our list is 1. So, we make the first digit of C something different, let's say 2. The second digit of the second number on our list is 1. So, we make the second digit of C something different, again 2. The third digit of the third number on our list is 4. So, we make the third digit of C something different, let's say 1. The fourth digit of the fourth number on our list is 3. So, we make the fourth digit of C something different, let's say 1. We continue this process forever, creating our new number C, which might start 0.2211. Now comes the crucial insight. Is our newly constructed number C present anywhere on our original, supposedly complete list? The answer must be no. Why? Because by its very construction, C is guaranteed to be different from every single number on the list. It's different from the first number on the list because its first decimal place is different. It's different from the second number on the list because its second decimal place is different. It's different from the nth number on the list because its nth decimal place is different. We have constructed a real number between 0 and 1 that, by definition, cannot be on our list. But this leads to a direct contradiction. We started with the assumption that our list was complete, that it contained all the real numbers. Yet, we have just constructed a real number that is provably not on the list. Therefore, our initial assumption must have been false. It is logically impossible to create a complete, one-to-one list of all the real numbers. The set of real numbers cannot be counted or put into a one-to-one correspondence with the natural numbers. The conclusion is staggering. The infinity of the real numbers, the continuum, is a fundamentally larger, higher order of infinity than the countable infinity of the integers. This shattered the idea of a single infinity and opened up a whole new landscape of transfinite mathematics, with a hierarchy of different-sized infinities, Aleph numbers, which we may explore later. Cantor's diagonal argument proved that some infinities are simply bigger than others. This paradox, paradoxical in the sense that it defies the intuitive notion that all infinities are alike, is a profound mindfuck. It uses finite reasoning to prove something definitive about the structure of the infinite. It questions our ability to even conceive of the scale of certain mathematical objects. The set of points on a line is a thicker, denser infinity than the set of counting numbers that stretch on forever. The implications are vast, affecting the foundations of mathematics, logic, and computer science, e.g., demonstrating the existence of uncomputable numbers. As you allow your body and mind to fall asleep, let the elegance of Cantor's diagonal argument wash over you. Picture the infinite list of numbers, the diagonal path carving out a new creation, a number that proves the list's own incompleteness. Contemplate the idea of different sizes of infinity, a concept that stretches the imagination to its limits. Let go of the notion of a single, simple infinity. Find deep relaxation in the sheer vastness and unexpected structure of the mathematical universe Cantor revealed. A reality with infinities beyond infinities, a paradise of thought that is endlessly deep, endlessly mysterious, resting peacefully within the profound, layered, and beautiful structure of the infinite. Russell's paradox. Let us now descend into the very foundations of logic and mathematics, to confront a paradox so simple in its telling, yet so devastating in its implications, that it triggered a profound crisis at the heart of our quest for certainty. This is Russell's paradox, a puzzle that arises not from the complexities of physics or the ambiguities of the physical world, but from the seemingly innocent act of categorizing things into groups or sets. It reveals that the intuitive, common-sense way we think about collections can harbor a deep, self-referential contradiction when pushed into the realm of infinity. The paradox, discovered by the brilliant philosopher and mathematician Bertrand Russell, questions the very consistency of logical systems, revealing that language and logic, when turned upon themselves, can create irresolvable knots. It is a fundamental mindfuck that challenges the idea that we can ever create a perfectly complete and consistent map of abstract reality, inviting you to fall asleep pondering the limits of reason itself. To understand this paradox, we must first consider the simple idea of a set. A set is merely a collection of things. We can think of the set of all chairs, the set of all planets, or the set of all even numbers. Our intuition tells us that any well-defined property should be able to define a set. Now, let's consider the relationship a set can have with itself. Most sets we think of are normal, in that they do not contain themselves as a member. The set of all chairs, for instance, is not itself a chair. It's a concept, a collection. The set of all teacups is not a teacup. These are well-behaved, non-self-containing sets. However, one could, in the abstract, imagine strange sets that do contain themselves. Perhaps this set of all abstract ideas could be considered an abstract idea itself, and therefore a member of itself. Or this set of everything that is not a teacup certainly contains itself, since the set itself is not a teacup. In the late 19th and early 20th centuries, in the naive phase of set theory, this distinction was noted but not seen as particularly problematic. It was assumed that sets could be cleanly divided into two categories: those that contain themselves and those that do not. Russell's genius was to take this simple division and use it to construct a conceptual bomb. He asked us to consider forming a very specific set, let's call it R. The set R is defined as follows: the set of all sets that do not contain themselves. It is the collection of all the normal sets. The set of chairs would be in R. The set of planets would be in R. But the set of everything that is not a teacup would not be in R. The definition seems clear and precise. Now comes the devastating paradoxical question. What about the set R itself? Does R contain itself as a member? Let's follow the two logical paths, both of which lead to contradiction. First, let's assume that R is a member of itself. If we posit that R is in R, then it must satisfy the condition for membership in R. The condition for membership in R is to be a set that does not contain itself. So, if R is a member of R, it logically follows that R must not be a member of R. This is a direct, undeniable contradiction. Our initial assumption must be false. So, let's try the only other possibility. Assume that R is not a member of itself. If R is not a member of R, then it satisfies the very definition for being included in R, because R is the set of all sets that are not members of themselves. So, if R is not a member of R, it logically follows that it must be a member of R. This too is a direct contradiction. We are trapped in an inescapable logical loop. If R contains itself, it doesn't. If it doesn't contain itself, it does. The question of whether R is a member of R is logically undecidable and paradoxical. The very existence of such a set, which seemed definable using intuitive principles, breaks the fundamental law of non-contradiction. This demonstrated that the naive assumption underlying set theory at the time, the principle of unrestricted comprehension, which held that any coherent property could define a set, was fundamentally flawed and inconsistent. The historical impact of this discovery was immense. It struck at the heart of the logicist project, led by thinkers like Gottlob Frege, which aimed to demonstrate that all of mathematics could be grounded in and derived from the seemingly solid foundations of pure logic. Russell famously wrote a letter to Frege, just as Frege was about to publish the second volume of his life's work, gently explaining the paradox. Frege was devastated, realizing that the very foundation of his system was inconsistent. The discovery of Russell's paradox initiated a foundational crisis in mathematics, forcing a complete rethinking of how sets and logic should be formulated to avoid such self-referential contradictions. The eventual solution was the development of axiomatic set theory, most notably Zermelo-Fraenkel set theory (ZFC), which is the standard foundation for modern mathematics. ZFC avoids the paradox by introducing a set of carefully crafted axioms, or rules, that restrict how sets can be formed. It essentially outlaws the creation of sets like Russell's R. For instance, the axiom of regularity explicitly forbids any set from being a member of itself, preventing the self-containment loop from the start. In essence, the paradox wasn't solved in its natural language form. It was banned from the formal system. We built a logical fence around the paradoxical territory to preserve the consistency of the rest of mathematics. This resolution, however, is itself philosophically profound. It means that our most rigorous system of thought, mathematics, rests upon foundational axioms chosen specifically to avoid known paradoxes. It suggests that consistency must be carefully engineered, not naively assumed. The mindfuck lingers. Does Russell's set exist, in some conceptual sense, even if our formal systems forbid it? What other paradoxes might lurk, undiscovered, within the foundations of our reasoning? Russell's paradox serves as an eternal reminder of the limitations of formal systems, the dangers of unrestricted self-reference, and the humbling fact that even in the purest realm of logic, we cannot take consistency for granted. It questions the very ability of any system to fully and consistently describe itself. As you continue your journey towards sleep, let the looping logic of Russell's paradox gently unwind in your mind. A set defined by what it excludes, which then cannot decide whether to include or exclude itself. Feel the beautiful, frustrating impossibility of the concept. Appreciate this profound mystery not as a failure of logic, but as a deep insight into its boundaries. Find deep relaxation in letting go of the dream of perfect, self-contained certainty. Acknowledge that even our most rigorous systems are built on choices made to avoid the abyss of contradiction. Resting peacefully within the profound, elegant, and ultimately foundational puzzle of self-reference. The Continuum Hypothesis. Having seen George Cantor's diagonal argument reveal the astonishing fact that there are different sizes of infinity, we are now prepared to venture into one of the most profound and mysterious questions that emerged from his work, a question that has haunted the foundations of mathematics for over a century. We know of the countable infinity of the natural numbers, 1, 2, 3, which Cantor called Aleph Null. We also know of the larger, uncountable infinity of the real numbers, the continuum, which includes all points on a line, which has a size of 2 to the power of Aleph Null. The natural, burning question that arises is this: is there anything in between? Is there an infinite set whose size is strictly larger than the infinity of the integers, but strictly smaller than the infinity of the real numbers? The proposition that no such intermediate infinity exists is known as the Continuum Hypothesis, ch. For decades, mathematicians tried to prove it true or prove it false, assuming it must be one or the other. The eventual resolution, however, was a mindfuck of a completely different order, revealing something deeply strange about the nature of mathematical truth itself. The mystery of the Continuum Hypothesis questions not just the structure of infinity, but whether our fundamental axioms of mathematics are capable of describing a single, unique mathematical reality, inviting profound contemplation as you fall asleep. Let's first appreciate the scale of the question. Cantor had successfully built a paradise of transfinite numbers, a hierarchy of ever larger infinities. He had identified the first step in this hierarchy, Aleph Null, the size of the set of all integers. He had also identified a much larger infinity, the size of the continuum. He naturally labeled the next size of infinity after Aleph Null as Aleph 1. The Continuum Hypothesis, in its more formal language, is simply the assertion that the size of the continuum is Aleph 1. In other words, there are no in-between sizes of infinity. The continuum is the very next step up from the integers. This seemed like a reasonable, elegant proposition, and Cantor himself spent years of his life trying desperately to prove it. He failed, and the struggle is said to have contributed to his mental health problems. The question was so fundamental that it was placed first on David Hilbert's famous list of 23 unsolved problems in mathematics in the year 1900, highlighting its central importance. The breakthrough, or rather, the profound complication, came in two stages from two different logicians. In 1940, Kurt Gödel, the same logician who gave us the incompleteness theorems, made a startling discovery. He showed that the continuum hypothesis cannot be disproved using the standard axioms of set theory, ZFC, the foundation upon which most modern mathematics is built. He did this by constructing a specific model, or mathematical universe, called the constructible universe L, in which all the standard axioms of ZFC are true, and the continuum hypothesis is also true. Since he had found a consistent scenario where CH is true, it meant that no one could ever use the ZFC axioms to prove that CH is false, because that would imply the axioms themselves are inconsistent. This was a monumental result, but it was only half the story. It left open the possibility that one could still prove CH to be true from the axioms. The final, reality-bending piece of the puzzle was delivered by mathematician Paul Cohen in 1963, for which he won the Fields Medal. Cohen developed a powerful new technique called forcing to show the opposite. He demonstrated that the continuum hypothesis also cannot be proved from the standard axioms of set theory. He did this by constructing different, alternative models of set theory where all the ZFC axioms are true, but in these models the continuum hypothesis is false. He showed that you could consistently construct mathematical universes where there are many, even infinitely many, different sizes of infinity nestled between the size of the integers and the size of the real numbers. Taken together, the work of Gödel and Cohen produced one of the most profound results in the history of logic. The continuum hypothesis is independent of the standard ZFC axioms of mathematics. This means that our fundamental axioms, the very bedrock upon which we build mathematics, are simply not powerful enough to decide the question one way or the other. The axioms allow for multiple, mutually contradictory mathematical realities. They allow for a universe where CH is true, and they allow for universes where CH is false. The question, is there an infinity between the integers and the reals, cannot be answered with a simple yes or no from within our standard mathematical framework. It is an undecidable statement. This is the ultimate mindfuck of the continuum hypothesis. It's not just that we don't know the answer, it's that there is no single answer to be found using our current foundations. This profoundly questions the very nature of mathematical truth and existence. For Platonists who believe in a single, objective mathematical reality where every well-formed statement is either true or false, this is a crisis. If there is one true mathematical universe, why can't our axioms tell us about its fundamental structure? Does it mean our axioms are deficient, that we need to find new, more powerful axioms that will finally settle the question? Or does it, as others argue, suggest that Platonism is wrong, and there isn't one single mathematical reality? Perhaps there is a multiverse of different set-theoretic universes, each with different properties, and we are simply free to explore whichever one we choose by adopting different axioms. This situation reveals the limits of formal systems in a way that is even more concrete than Gödel's more abstract incompleteness theorems. It presents a specific, meaningful mathematical question about the structure of infinity that our foundational system is powerless to answer. It's as if we have a perfect map of a continent's coastline, but the map contains absolutely no information about whether there is a giant mountain range in the interior. As you continue to fall asleep, let your mind float in this strange space of mathematical undecidability. Picture the line of integers, Aleph null, stretching out infinitely. Picture the dense, continuous line of real numbers, a vastly larger infinity. And now contemplate the gap between them. Is it empty of other infinities or teeming with them? The continuum hypothesis tells us our most fundamental rules cannot decide. The question itself hangs suspended, independent of our logic. This is not a failure, but a revelation about the richness and mystery of the abstract realm. It questions the very idea of a single, knowable mathematical truth. Find deep relaxation in this ultimate uncertainty, in the freedom of knowing that even in the world of pure reason, there are vast territories where truth is not fixed, but a matter of which universe of thought you choose to inhabit, resting peacefully, unbound by the need for a single answer, within the profound, open mystery of the continuum. Gabriel's horn/Torricelli's trumpet. Let us now turn to a paradox that brings the strangeness of infinity into the realm of geometry, creating a seemingly impossible object that defies our most basic physical intuitions about space, area, and volume. This is the mind-bending thought experiment known as Gabriel's horn, or sometimes Torricelli's trumpet. It describes a three-dimensional shape that has a finite volume, meaning it could, in theory, be filled with a finite amount of paint, yet possesses an infinite surface area, meaning you could never, ever finish painting its inner surface. How can a container that holds a limited amount of stuff have a boundary that stretches on forever? This bizarre mathematical object challenges the relationship between dimensions and measurement, questioning our common-sense understanding of how space works and revealing the profound ways that infinity can be tamed in one dimension while remaining wild and unbounded in another. Let this impossible shape twist gently in your mind's eye as you fall asleep. To visualize Gabriel's horn, imagine we start with a simple curve on a two-dimensional graph. We take the curve defined by the equation y equals 1/x, and we only look at the part of the curve starting from x equals 1 and extending infinitely to the right. This curve starts at a height of 1 and gets progressively closer and closer to the x-axis as x gets larger, but it never actually touches it. Now, imagine taking this infinitely long curve and rotating it around the x-axis, sweeping it through three-dimensional space. The shape you create is a long, tapering horn or trumpet, with a wide opening at one end that narrows infinitely, stretching on forever without ever fully closing. This is Gabriel's horn. The paradox arises when we use the methods of calculus to measure two of its properties, its volume and its surface area. The calculation for the volume, the amount of space inside the horn, involves summing up the areas of an infinite number of infinitesimally thin circular disks along its length. This calculation results in an infinite sum that, much like the convergent series we explored earlier, adds up to a surprising, perfectly finite result. The volume of Gabriel's horn is exactly pi. This means you could, in theory, fill the entire horn with just over 3 cubic units of paint. The horn has a definite, limited capacity. Now, let's calculate the surface area of the horn's interior. This involves summing up the circumferences of those same infinite number of infinitesimally thin disks. When we perform this calculation, the resulting infinite sum does not converge. It diverges, meaning it grows without bound towards infinity. The inner surface of the horn has an infinite area. Here, laid bare, is the astonishing mindfuck. We have a single object that we can completely fill with a finite amount of paint, volume equals pi, but we do not have enough paint in the entire universe to cover its inner surface, surface area equals infinity. This is the painter's paradox. If you pour the paint in, every single point on the infinite inner surface becomes coated with paint. Yet, if you try to apply the paint with even the thinnest possible brush, you would never finish the task. The horn holds a finite amount, but its inner lining is endless. How can we resolve this seeming contradiction? The resolution lies in recognizing the difference between mathematical idealizations and physical reality, and in understanding the subtleties of dimensionality. Mathematically, the paradox is perfectly sound. It demonstrates how a quantity can decrease quickly enough for its volume-related sum, involving r squared, to converge, while its area-related sum, involving just r, diverges. It's a beautiful, if strange, consequence of how calculus handles infinite series. The physical paradox, the painter's paradox, is often resolved by considering the nature of paint. A real painter uses paint that has a certain thickness. Once the horn tapers down to a radius smaller than the radius of a single paint molecule, the physical analogy breaks down. You simply couldn't get the paint to coat the surface in a layer of a certain thickness anymore. In essence, the physical world, being made of discrete atoms and molecules rather than infinitely divisible points, doesn't allow for the construction of a true Gabriel's horn. However, this physical resolution does not diminish the profound conceptual challenge posed by the mathematical object itself. It still exists as a consistent idea within the world of pure thought, and its properties question our intuitive understanding of space. It forces us to decouple the concepts of volume and surface area, which we normally see as closely linked. We assume that if something has a finite volume, it must have a finite boundary. Gabriel's horn proves this intuition wrong. It shows that an object can be bounded in one sense, volume, while being unbounded in another, surface area. This paradox is a powerful illustration of the strangeness that infinity introduces into geometry. It's a reminder that mathematical reality can accommodate objects with properties that seem physically impossible. It challenges us to trust the results of logical and mathematical reasoning, even when those results violently contradict our lived experience and sensory intuition. It's a testament to the fact that the universe of mathematics is far larger and stranger than the universe of physical objects we can hold in our hands. It's a perfectly defined object that is simultaneously finite and infinite. As you continue to relax deeply, let the impossible shape of Gabriel's horn gently form in your imagination. See its wide opening, and picture its long, elegant taper stretching out endlessly, getting ever closer to a central line but never touching. Imagine pouring a finite amount of liquid light into its opening, watching it fill the entire finite volume. And yet, simultaneously, know that the inner surface this light touches is infinite in its expanse. Let this paradox dissolve your rigid assumptions about space and containment. Find peace in the strange beauty of this conceptual object. a finite vessel holding an infinite surface, a testament to the mind-bending elegance of mathematical thought, resting calmly within the impossible geometry of the infinite. Supertasks. We return now to the territory of Zeno's paradoxes, but with a modern philosophical lens, to explore the concept of a supertask. A supertask is a hypothetical task that consists of a countably infinite sequence of distinct actions or operations that are completed in a finite amount of time. We saw the mathematical possibility of this in the idea of a convergent series. The sum of an infinite number of ever-decreasing time intervals can be finite. For example, performing a task in half a minute, then the next in a quarter of a minute, the next in an eighth, and so on, would result in completing an infinite number of tasks in exactly 1 minute. While mathematically coherent, the question of whether a supertask is physically or even logically possible presents a series of profound paradoxes and mind-bending puzzles. Can infinity truly be completed? What is the state of the system at the precise moment the finite time limit is reached? The concept of the supertask forces us to confront the boundary between mathematical abstraction and physical or logical possibility, questioning our understanding of causality, continuity, and the nature of a completed infinite process, inviting deep contemplation as you fall asleep. Let's first establish the conceptual landscape. The idea of a supertask is a direct confrontation with our intuition that an infinite process must require an infinite amount of time. The mathematical framework of convergent series provides the license to even consider the possibility. It gives us a model where an endless sequence of events can be mapped onto a finite interval of time. The Zeno Paradoxes of the dichotomy and of Achilles and the tortoise are, in essence, descriptions of supertasks, traversing an infinite number of points. Calculus's limit-based solution essentially says, yes, these supertasks are completed. But this mathematical answer doesn't satisfy all the philosophical and logical quandaries that arise when we try to imagine the process itself in detail. The physical objections are often the most immediate. Performing a physical supertask like flipping a switch an infinite number of times would seem to require infinite energy, and the moving parts would need to travel at infinite speeds as the time intervals approach zero, violating known physical laws like the theory of relativity. From a purely physical standpoint, most would agree that supertasks are impossible for beings like us in the universe as we know it. However, the more profound paradoxes emerge when we set aside the physical limitations and consider the logical possibility. Let's assume, for the sake of the thought experiment, that physical constraints are not an issue. Can a supertask be described in a logically coherent way? This is where the puzzles begin. The core problem often lies in determining the state of the system at the exact moment the supertask is completed. Since the sequence of actions is infinite, there is no last action. The state of the system is determined by an endless series of operations, none of which is the final one. This leads to logical indeterminacy. This problem is most famously illustrated by a specific type of supertask puzzle, Thomson's lamp, which we will explore in detail in our next segment. But we can consider the general problem here. Imagine a ball being moved back and forth between 2 points, with each traversal taking half the time of the previous one, completing the infinite journey in, say, 2 minutes. At the end of the 2 minutes, where is the ball? Its position at any moment before the 2-minute mark is well defined. But at the final instant, there is no final position it was moving towards, as the back-and-forth motion has no final step. The mathematical function describing its position has no defined limit at that point. The end state is logically undefined by the description of the task. This questions our very understanding of what it means to complete an infinite process. Can we truly speak of a state after an infinite sequence if that sequence has no final member to determine the final state? The concept of a supertask seems to create a limit point in time where the past history of the system, despite being infinitely detailed, fails to logically entail a specific state of affairs. Furthermore, supertasks can be used to construct scenarios that seem to lead to contradictions or impossible outcomes. Consider a genie supertask. A genie grants you a wish but says you must choose a positive integer, 1, 2, 3. You will wait 1 minute. If you haven't chosen by then, your wish is gone. You decide to simply count upwards, 1, 2, 3, to delay. But since the set of integers is countably infinite, you could theoretically count all of them in a finite time if you did it as a supertask, counting 1 in 1/2 minute, 2 in 1/4 minute, etc. If you complete this supertask in 1 minute, you will have named every positive integer. What number have you chosen for the genie? There is no largest integer, so you have not chosen a final number. You have completed the task of naming all of them, yet failed to fulfill the condition of choosing one. The mind fuck of the supertask lies in this collision between a mathematically convergent timeline and a logically indeterminate end state. Our minds can grasp the idea of the time interval shrinking to zero and the total time being finite. But we cannot grasp what it means to have finished an endless list of actions. It feels like a contradiction in terms, to complete something that, by definition, has no end. This mystery pushes us to think deeply about the nature of time and causality. Is time continuous and infinitely divisible, allowing for the theoretical possibility of supertasks? Or is it discrete, quantized, making supertasks impossible? If supertasks are logically possible, does it mean that there can be events with fully determined pasts that nevertheless have indeterminate presents? This would be a profound challenge to determinism and our understanding of physical law. It suggests that completing an infinity might create a genuine break in the causal chain. As you continue to fall asleep, let the idea of the supertask gently play in your mind. An infinite number of actions compressed into a finite moment, a countdown that never reaches zero but somehow finishes. Contemplate the runner crossing an infinite number of halfway points, the lamp being switched endlessly. Do not struggle with the final state. Instead, appreciate the paradox as an exploration of the very concept of completion when applied to the infinite. Find deep relaxation in the idea of an endless process held within a finite boundary, a mind-bending concept that blurs the line between the eternal and the momentary, resting peacefully within the profound, logical puzzle of a finished infinity. Thomson's lamp paradox. Having contemplated the general possibility of supertasks, infinite actions in finite time, let us now focus on the most elegant and perplexing example, a thought experiment that lays bare the logical paradox at the heart of completing an infinite sequence. This is Thomson's lamp paradox, devised by philosopher James F. Thomson. It takes the abstract concept of a supertask and attaches it to a simple binary system, a lamp that can be either on or off, to reveal a profound logical indeterminacy. It's a powerful logic puzzle that asks a simple question about the final state of an infinitely switched lamp, a question that, upon close inspection, seems to have no possible answer. This mindfuck paradox is not about the physics of flipping a switch. It is a pure exploration of logic and infinity, questioning whether the concept of a final state is even meaningful after an infinite series of alternating actions. Let the simple image of this flickering lamp guide your mind into a state of deep, contemplative relaxation as you fall asleep. Here is the setup in its elegant simplicity. We have a special lamp with a toggle switch. The lamp begins in the off state. We are going to perform a supertask over a period of exactly 2 minutes. At the end of 1 minute, that is, after 1 minute has passed, we switch the lamp on. At the end of the next half minute, at the 1.5 minute mark, we switch it off. At the end of the next quarter minute, at the 1.75 minute mark, we switch it on. We continue this process, switching the lamp at the halfway point of each remaining time interval. The sequence of time intervals is 1 minute, then 1/2 minute, then 1 quarter, then January 8th, and so on. This is a convergent geometric series whose sum is exactly 2 minutes. So, at the precise moment that 2 minutes have elapsed, the infinite sequence of switch flipping actions has been completed. The question is, at the end of the 2 minutes, is the lamp on or off? Let us try to reason our way to an answer. Our intuition might try to find a pattern. The lamp is switched on at time 1, 1.75, etc., and off at time 1.5, 1.875, etc. We perform an infinite number of on actions and an infinite number of off actions. Does this mean the state is ambiguous? Let's try to be more rigorous. We could argue that the lamp must be on. For every time we turn the lamp off, there is always a subsequent time at which we turn it back on. For the off switch at 1.5 minutes, there's the on switch at 1.75. For every off switch, there is a later on switch. This line of thought might suggest that on is the final state. But we can construct an equally compelling argument that the lamp must be off. For every time we turn the lamp on, there is always a subsequent time at which we turn it back off. For the on switch at 1 minute, there's the off switch at 1.5. For the on switch at 1.75, there's the off switch at 1.875. For every single on action, it is followed by an off action. This seems to suggest that off must be the final state. The core of the paradox is that both of these arguments are flawed because they rely on the concept of a last action. In an infinite sequence of actions like this, there is no last switch. There is no final member of the sequence. The set of actions, on, off, has no final element to determine the final state of the lamp. Every on is followed by an off, and every off is followed by an on. To ask what the last switch was is to ask a meaningless question about an infinite sequence. Therefore, at the precise moment the 2 minutes are up, the state of the lamp appears to be logically indeterminate. The description of the task, while perfectly defining the state of the lamp at any moment before the 2-minute mark, provides absolutely no information to determine its state at the 2-minute mark. The logical chain that defines the lamp's state at each step of the sequence does not extend to the limit point itself. The past history of the system, even though it's infinitely detailed, fails to entail a final state. Thomson's lamp paradox is a powerful illustration of the limits of logic when applied to completed infinities. It is not a physical paradox. We cannot build such a lamp. It is a conceptual one. It shows that the concept of a supertask, while perhaps mathematically describable in terms of its duration, can lead to states of affairs that are not just unknown, but logically undefined. The problem isn't our inability to know if the lamp is on or off. The problem is that the very question might be incoherent. The conditions laid out simply do not define a final state. This mindfuck forces us to question what it means to complete an infinite process. Does completion imply a final state must exist? Thomson's paradox suggests that the answer might be no. It highlights a fundamental difference between approaching a limit and reaching it. For every point approaching the 2-minute mark, the lamp state is defined. But at the limit point itself, the definition provided by the sequence evaporates. It's a profound conceptual glitch, a void in logical consequence created by the structure of the supertask. This has deep philosophical implications for our understanding of infinity, causality, and logic. It suggests that even if we could manipulate time and perform infinite tasks, the resulting reality might contain fundamental indeterminacies, gaps in the causal fabric where the state of being is simply undefined. It challenges our assumption that every well-defined process must have a well-defined outcome. As you continue your journey towards sleep, let the image of Thomson's lamp flicker in your mind, on, off, faster and faster, approaching the final moment. And at that final instant, what is its state? Feel the logical tension, the inability of reason to provide an answer. Let the question dissolve into indeterminacy. The lamp is neither on nor off. The question itself is the paradox. Find deep relaxation in this logical void, in accepting that some perfectly described processes may not have perfectly describable outcomes. Embrace the mystery that lies at the limit of infinite action, resting peacefully in the quiet, undefined state beyond the final flicker. The St. Petersburg Paradox. Imagine you are invited to play a seemingly simple game of chance, a game with the potential for an immense, even limitless, reward. A fair coin will be tossed repeatedly until it lands on tails and the game ends. If tails appears on the first toss, you win $2. If it lands heads first, then tails, the payout doubles to $4. If it's heads, then tails, the payout doubles again to $8. The pot continues to double with every consecutive head, and your prize is determined by the toss that finally brings the game to a close. The question is, what is a fair price to pay to play this game? How much would you, a rational person, be willing to wager for one chance at this potentially enormous prize? Our intuition might suggest a modest amount, a few dollars, perhaps 10 or 20. Yet, the cold, hard logic of mathematics reveals a stunning and paradoxical answer. The expected value of this game is infinite. This profound clash between our intuitive sense of reasonable value and the mathematical calculation of average outcome is the St. Petersburg Paradox. It's a deep mindfuck that questions the very nature of rationality, value, and decision-making when the specter of infinity enters the equation, inviting you to fall asleep contemplating the chasm between mathematical expectation and human reality. Let's gently walk through the mathematics to understand how this infinite result arises. The expected value of a gamble is calculated by taking the value of each possible outcome, multiplying it by the probability of that outcome occurring, and then summing all those results together. In the St. Petersburg game, the possible outcomes and their probabilities are as follows. There is a 1 in 2 or 50% chance that the first toss is tails, in which case you win $2. The contribution to the expected value is 1/2, $2 equals $1. There is a 1 in 4 or 25% chance that the sequence is heads-tails, in which case you win $4. The contribution is 1/4, asterisk $4 equals $1. There is a 1 in 8 or 12.5% chance that the sequence is heads-tails, giving you $8. The contribution is 1/8, asterisk $8 equals $1. There is a 1 in 16 chance of winning $16, contributing 1/16, asterisk $16 equals $1. As you can see, this pattern continues forever. For any payout of 2 to the power of n dollars, the probability of achieving it is 1 over 2 to the power of n. The contribution to the expected value from every single possible outcome is exactly $1. To find the total expected value of the game, we must sum these contributions. 1 plus 1 plus 1 plus 1 plus 1, stretching on for an infinite number of possible outcomes. The sum of this infinite series is undeniably infinity. Herein lies the paradox. A purely rational agent, according to some classical economic theories, should be willing to pay up to the expected value to play a game. This would mean that it is rational to pay any finite amount of money, $1,000, $1 million, $1 billion, for a single chance to play. Yet this strikes us as absurd. No sane person would risk their life savings for this game. Our powerful intuition that this game isn't worth a huge amount directly contradicts the mathematical result. The paradox forces us to explore why our intuition and this formal calculation diverge so dramatically. The resolution lies in deconstructing the assumptions behind the calculation and recognizing the complexities of human psychology and real-world constraints, which pure mathematics can ignore. The first and most important solution was proposed by Daniel Bernoulli, and it introduces the concept of utility, a cornerstone of modern economics. Bernoulli argued that people do not value money in a linear fashion. They value the subjective usefulness or satisfaction it brings, and this is subject to diminishing marginal utility. What this means is that each additional dollar is worth slightly less to you than the one before it. The difference between having $0 and having $1 million is life-transforming. The difference between having $100 million and $101 million, while still nice, is far less impactful on your overall well-being. The subjective utility of the money does not increase linearly with its amount. It likely increases logarithmically. If we recalculate the expected value of the St. Petersburg game using utility instead of raw dollar amounts, the infinite series converges to a small, finite number. This is because the massive billion-dollar payouts, while numerically huge, contribute very little additional utility compared to the smaller, more likely payouts. Our intuition, it seems, is automatically performing a utility calculation, not an expected value calculation. It correctly assesses that the value of the game to our finite lives is finite. Another crucial factor is risk aversion. The St. Petersburg game is incredibly risky. There is a 50% chance you will only win $2, and a 75% chance you will win $4 or less. The astronomically high payouts that drive the expected value to infinity are also astronomically unlikely. To win just $1,024, you need a run of 9 consecutive heads, a probability of 1 in 512. Most people are naturally risk-averse and weigh the high probability of a small gain much more heavily than the vanishingly small probability of an enormous one. Our intuition recoils from paying a large sum for something that will most likely yield a paltry return. Furthermore, the paradox operates in a conceptual space of infinite resources, which is a physical impossibility. For the game to have an infinite expected value, the casino or person offering the bet must have an infinite bankroll, capable of paying out any conceivable prize, no matter how large. In reality, any game operator has finite resources. If we cap the maximum possible payout, say at $1 trillion, the expected value of the game immediately becomes finite and in fact quite small, around $40 in this case. The infinity in the calculation is an artifact of assuming a physically impossible scenario. The St. Petersburg Paradox is therefore a beautiful mindfuck that illuminates the gap between abstract mathematical models and applied human rationality. It doesn't prove that mathematics is wrong, but it proves that naively applying mathematical concepts like expected value, without considering psychological context like utility, risk aversion, and real-world constraints can lead to nonsensical conclusions. It questions the very definition of rational choice. Is it rational to follow a mathematical formula even when it defies all common sense? Or is true rationality the ability to integrate formal logic with an intuitive understanding of human value and physical limits? As you continue to fall asleep, contemplate the coin being tossed, heads, heads, heads. The potential prize doubling endlessly into a theoretical infinity, and yet feel your own intuitive sense of its small, finite worth. Acknowledge the profound wisdom in this intuition, its grasp of diminishing utility and real-world risk. The St. Petersburg Paradox reveals that value is not just a number. It is a deeply human, subjective experience. Find deep relaxation in the understanding that your own sense of what is reasonable has a profound logic of its own, a logic that can wisely temper the wild, untamed infinities of pure mathematics, resting peacefully, secure in a richer, more nuanced understanding of value. Aleph Numbers. Having seen George Cantor's diagonal argument shatter the intuitive notion that all infinities are the same size, we are now prepared to enter the strange and beautiful paradise he discovered. To navigate this new landscape of differing infinities, a new system of numbers was needed, numbers capable of describing the size or cardinality of infinite sets. These are the transfinite cardinal numbers, which Cantor named using the first letter of the Hebrew alphabet, Aleph. The Aleph numbers represent a ladder of infinities, a hierarchy stretching upwards from the smallest infinite size into realms of thought that are profoundly abstract and dizzyingly vast. Contemplating these numbers is an exercise in pure abstraction, a mind-bending journey that questions our finite concepts of quantity and number, revealing a universe of mathematical existence far beyond what our senses can perceive. Let the idea of counting beyond infinity gently expand your mind as you drift deeper into relaxation and towards sleep. The journey begins with the first step on the infinite ladder, the most familiar of the infinities, Aleph Null, written as. Aleph Null is defined as the cardinality of the set of all natural numbers, 1, 2, 3. It is the size of any set whose elements can be put into a perfect one-to-one correspondence with the counting numbers. This is the infinity of countable sets. As we saw in Galileo's paradox, many sets that seem smaller are actually this size. The set of all even numbers has a cardinality of Aleph Null. The set of all odd numbers, Aleph Null. The set of all prime numbers, Aleph Null. Even the set of all rational numbers, all fractions, which seem to be densely packed everywhere on the number line, can be ingeniously listed out and shown to have a cardinality of Aleph Null. This first Aleph number already possesses the deeply counterintuitive property that a part can be equal in size to the whole. It is the infinity of Hilbert's hotel, an endless but listable quantity. It represents the foundation of transfinite arithmetic. But Cantor's diagonal argument proved that not all infinite sets are countable. The set of all real numbers, the continuum of points on a line, is a larger, uncountable infinity. This means there must be a next size of infinity, a cardinal number that is larger than Aleph Null. Cantor defined this next, higher infinity as Aleph 1. By definition, Aleph 1 is the cardinality of the smallest infinite set that is larger than the set of natural numbers. It represents the next rung on the ladder of infinities. It is the size of the set of all possible ways to well-order the natural numbers. While Aleph Null is the infinity we can count or list, Aleph 1 is the first infinity that we cannot. It is the beginning of the uncountable. This leads directly to one of the most profound mysteries in modern mathematics, the Continuum Hypothesis, which we explored previously. The hypothesis is simply the question: is the size of the continuum of real numbers equal to Aleph 1? In other words, is the infinity of the real number line the very next size up from the infinity of the integers, or is it much larger? The mind-bending resolution from the work of Gödel and Cohen is that this question is undecidable within our standard mathematical framework, ZFC. This means we have a clearly defined concept, Aleph 1, representing the next infinity, but we cannot prove whether the familiar continuum is that next infinity, or if it might be Aleph 2, Aleph 17, or something else entirely. The Aleph numbers give us a beautifully ordered ladder, but the familiar infinity of the real numbers refuses to tell us which rung it stands on. This undecidability itself questions the nature of mathematical truth, suggesting a plurality of possible mathematical universes. And the ladder of Aleph numbers does not stop there. The principles of set theory guarantee a never-ending hierarchy. Cantor's theorem proves that for any set, the set of all its possible subsets, its power set, is always strictly larger than the original set. This applies to infinite sets as well. So, starting with the set of natural numbers, size Aleph Null, we can consider the set of all its subsets. This new set has a cardinality that is strictly larger than Aleph null. This gives us another, even larger infinity. We can then take the power set of that set to generate a yet larger infinity and so on forever. This process generates an endless tower of infinities, Aleph null, Aleph 1, Aleph 2, Aleph 3, continuing on without end. There is no largest infinity. For any infinite size you can name, there is always a larger one. The concept of infinity itself is infinite. This hierarchy is a breathtaking feat of human abstraction. The Aleph numbers are not numbers we use to count physical objects. They are pure concepts, tools for measuring the immeasurable, for comparing the sizes of collections that our minds can barely comprehend. They exist within the consistent world of formal mathematics, but their relationship to physical reality is tenuous at best. They represent a universe of pure thought, a paradise, as David Hilbert called it, from which mathematicians should not be driven. Contemplating them is a form of deep meditation on structure and quantity, divorced from tangible experience. It's a mind fuck that forces us to expand our definition of number into realms of unimaginable scale. As you continue to fall asleep, let your mind gently ascend the ladder of Aleph numbers. Begin with Aleph null, the countable infinity of footsteps on an endless path. Then try to conceive of Aleph 1, the first shore beyond that countable ocean, an uncountable infinity whose exact nature relative to our own world remains a mystery. Then picture Aleph 2, Aleph 3, an endless tower of infinities, each one unimaginably vaster than the last. Let go of the need to visualize these concepts perfectly. Their existence as logically coherent ideas is the wonder. Find deep relaxation in the sheer scale of this conceptual cosmos. A universe of thought where size itself becomes infinite in its variety, resting peacefully within the vast, silent, and beautifully ordered hierarchy of Cantor's transfinite paradise. The concept of potential versus actual infinity. Throughout our journey tonight, we have repeatedly invoked the term infinity, often treating it as a concrete, existing quantity. Yet, for over 2,000 years of philosophical and mathematical thought, this very idea was considered absurd and paradoxical. To navigate the treacherous waters of the infinite, thinkers historically relied on a crucial distinction, a conceptual divide that separates a tame and acceptable infinity from a wild and dangerous one. This is the distinction between potential infinity and actual infinity. Understanding this historical and philosophical conflict is key to appreciating the revolutionary nature of modern mathematics and the deep mindfuck that occurs when we are asked to accept the existence of a completed, actual infinity. This distinction questions the very ontological status of infinity. Is it merely a process that never ends, or is it a definite, existing object? The tension between these two views is a profound mystery about the relationship between our minds, our mathematical systems, and reality itself, inviting deep relaxation through the contemplation of these two different modes of endlessness as you fall asleep. Let's first explore potential infinity. This is the classical conception, most clearly articulated by Aristotle, that dominated Western thought for millennia. Potential infinity refers to infinity as a perpetual process, a possibility of endless continuation. It is infinity as a verb, as a becoming. For example, you can always count one more number. The sequence of natural numbers is potentially infinite because the process of counting never has to stop. You can always divide a line segment in half. Any finite length is potentially infinitely divisible because the process of division can always be repeated. According to this view, we never encounter or deal with a completed, infinite set. The collection of all numbers is not considered a single existing object, but rather an endless potential. This view is intuitively comfortable. It aligns with our experience of processes in time. It avoids many of the paradoxes we've discussed, or rather, it dissolves them by denying their premise. Zeno's paradoxes, for instance, lose their bite if you can't treat the infinite number of required steps as a completed, actual set of tasks that must be finished. Hilbert's hotel is impossible because an actually infinite number of rooms cannot exist as a completed totality. For Aristotle and his followers, actual infinity was a contradiction in terms, a logical monstrosity. Now let's turn to actual infinity. This is the radical, counterintuitive idea that an infinite set can exist as a single, complete, static entity. It is infinity as a noun, as a being. The set of all natural numbers, 1, 2, 3, considered as a finished object, is an actual infinity. The set of all points on a line segment is another. It was George Cantor's work in the late 19th century that forced mathematics to take actual infinity seriously. He treated infinite sets as definite mathematical objects and began to explore their properties, leading to his discovery of transfinite numbers like the Aleph numbers and the proof that there are different sizes of actual infinity. This was a revolution. It meant that paradoxes like Galileo's, where a part, the perfect squares, is the same size as the whole, the natural numbers, were not absurdities to be avoided, but were in fact defining properties of these strange new objects. Hilbert's hotel is a thought experiment designed specifically to build intuition about the bizarre but consistent behavior of an actually infinite set. The conflict between these two conceptions, potential versus actual infinity, represents one of the most significant philosophical shifts in the history of mathematics. Cantor's embrace of actual infinity was met with fierce resistance from many of his contemporaries. Mathematicians like Leopold Kronecker famously declared, "God made the integers, all else is the work of man," expressing a deep distrust of these new non-intuitive infinite objects. The philosopher Henri Poincaré called Cantor's set theory a disease from which mathematics would one day recover. They saw it as a departure from the solid ground of finite human intuition into a realm of meaningless theological speculation. They were champions of the potential infinity perspective, believing mathematics should be grounded in what can be finitely constructed or conceptualized through a step-by-step process. The mind-fuck of this distinction lies in the chasm it reveals between our intuitive experience and the demands of formal consistency. Our direct experience of the world is one of finite objects and ongoing processes. Potential infinity aligns with this. Actual infinity, however, is a purely conceptual leap. We never experience a completed infinite set through our senses. Yet, this very concept proved essential for the development of modern mathematics, providing the foundations for calculus, analysis, and topology. Accepting actual infinity requires a leap of intellectual faith, a willingness to trust the consequences of formal logic even when they violently contradict our ingrained intuitions. The debate continues to echo in modern physics and cosmology. When we ask if the universe is spatially infinite, we are asking if it contains an actual infinity of locations or stars. When physicists grapple with singularities, they are confronting the appearance of actual physical infinities in their equations, which most believe signals a breakdown of the theory. The question of whether spacetime is continuous, implying an actual infinity of points, or discrete, quantized, is a debate about whether physical reality contains actual infinitesimals. The philosophical tension between potential and actual infinity is thus replayed in our scientific attempts to model reality. This mystery forces us to question the relationship between mathematics and the physical world. Is mathematics a description of reality, or a free creation of the human mind? If it's a creation, are we free to create and use concepts like actual infinity as long as they are internally consistent, regardless of whether they correspond to anything physical? If it's a description, does the success of theories using actual infinity imply that such infinities might actually exist in some form? As you continue to fall asleep, let the two concepts of infinity gently flow and diverge in your mind. Picture potential infinity as an endless road stretching to the horizon, a journey that never ends. Now, picture actual infinity as holding the entire endless road in your mind at once, as a single, complete object. Feel the profound shift in perspective from endless process to completed totality. Acknowledge the deep philosophical struggle this shift represents. Find deep relaxation in understanding that even the concept of infinity is not one, but two fundamentally different ideas, a source of centuries of debate and discovery, resting peacefully within the vast, conceptual space between what can be continued forever and what can exist all at once. Infinity in cosmology. Having journeyed through the abstract and formal landscapes of mathematical infinity, we now cast our gaze outward, to the grandest stage of all, the cosmos. We ask a question that bridges the gap between pure thought and physical reality: is the universe itself infinite? This is not just a question of scale, it's a question with profound, almost terrifying philosophical implications for our place in existence. Does space stretch on forever, containing an endless number of galaxies, stars, and perhaps even copies of ourselves? Or is it finite, vast, but ultimately bounded? Did time have a beginning, or has the universe existed in some form for an eternity? The application of the concept of infinity to cosmology generates some of the most staggering and mind-bending scenarios imaginable, questioning our uniqueness, the nature of cosmic origins, and the ultimate fate of all things. Let the unimaginable scale of the cosmos gently cradle your mind as you fall asleep. Let's first consider spatial infinity. Our best current cosmological models, based on Einstein's theory of general relativity and observations of the cosmic microwave background radiation, suggest that the universe is geometrically flat or very close to it. In the standard models, a flat universe is an infinite universe. If you were to travel in a straight line in any direction, you would travel forever, never returning to your starting point and never reaching an edge. While our observable universe is finite, a sphere about 93 billion light-years in diameter, representing the distance light has had time to travel to us since the Big Bang, the universe as a whole likely extends infinitely beyond what we can see. The implications of a spatially infinite universe are staggering and represent a true mindfuck. If the universe is infinite and the distribution of matter and energy is roughly uniform on large scales, as observations suggest, then any given volume of space with a specific arrangement of particles must, by sheer statistical probability, repeat itself elsewhere. And in an infinite universe, it must repeat itself an infinite number of times. This leads to the concept of the patchwork, or level 1 multiverse. It means that somewhere out there, far beyond our observable horizon, there is another galaxy, another solar system, another Earth, and another person who is an exact quantum-for-quantum duplicate of you, living a life identical to yours up to this very moment. And it doesn't stop there. There would also be an infinite number of regions where your life is almost identical, but with one tiny difference. You chose a different path this morning, or said something slightly different in a conversation yesterday. And there would be infinite regions where your life is wildly different. Every possible permutation of your existence that is not forbidden by the laws of physics would be realized somewhere out there in the infinite expanse. This radically questions our sense of individuality and uniqueness. What does it mean to be you if there are infinite copies? Does this affect the meaning of your choices, your struggles, your triumphs, if they are all being played out an infinite number of times across the cosmos? This is a direct consequence of combining standard cosmological models with the assumption of spatial infinity. Now let's consider temporal infinity. Did time itself have a beginning? The standard Big Bang model describes the universe expanding from an incredibly hot, dense state about 13.8 billion years ago. This is often thought of as the beginning of time. But what came before the Big Bang? The singularity predicted at the very beginning is a point where our current laws of physics break down, an infinity that signals the limit of our knowledge. Some cosmological models propose ways to avoid a true beginning. Eternal inflation theory suggests that our observable universe is just one bubble that nucleated out of a larger, eternally inflating spacetime multiverse. New bubble universes are constantly being born from this inflating background, meaning the multiverse as a whole might be eternal, with no beginning. Cyclical models like the Big Bounce propose that our universe undergoes endless cycles of expansion and contraction. Our Big Bang might have been the bounce that followed the collapse of a previous universe, a cycle that has been repeating for an eternity past and will continue for an eternity future. In these scenarios, existence itself has no ultimate origin point. It is temporally infinite. The future, too, might be infinite. Current observations of dark energy suggest the universe's expansion is accelerating. If this continues, the ultimate fate might be a big freeze, or heat death, where the universe expands forever, becoming increasingly cold, dark, and empty as all stars burn out and matter decays. This is a vision of an infinitely long, but ultimately desolate, future. The appearance of infinity in our cosmological models, whether in space, time, or the singularities of black holes and the Big Bang, consistently pushes our theories to their breaking points and our minds to the edge of comprehension. It forces us to ask whether these infinities are features of physical reality or artifacts of our incomplete mathematical descriptions. Is space really a continuous, infinite expanse, or is that just the best model our minds, using calculus, can create? The mystery of the relationship between mathematical infinity and physical infinity is one of the deepest problems in science. As you continue your journey into deep relaxation, allow your sense of scale to dissolve. Picture yourself as a tiny point of awareness in a universe that might stretch on forever, containing infinite copies of your world, your life. Imagine time flowing not from a single beginning, but as one cycle in an eternal series of breaths, an endless cosmic ocean. Let the staggering scale of cosmological infinity gently diminish the weight of your finite concerns. Find peace in this cosmic perspective. a sense of being part of a vast, mysterious, and perhaps boundless tapestry of existence. Acknowledge the profound mindfuck that your unique life might be one of an infinite number, and then let that thought go, returning to the simple, singular reality of this present moment, resting peacefully, a finite consciousness adrift in an infinite, or perhaps just unimaginably vast, cosmos. Infinity in physics. Having explored the abstract and often paradoxical nature of infinity in the realm of pure mathematics, let us now bring this confounding concept back into the physical world. In physics, the appearance of infinity within an equation is often not a sign of a profound new reality, but rather a warning, a red flag indicating that our current theory is breaking down, that its language is no longer sufficient to describe the reality it is attempting to model. These problematic infinities, often appearing in the form of singularities or in calculations within quantum field theory, represent the extreme edges of our understanding of the universe. Yet, the way physicists grapple with them, through ingenious, if sometimes controversial, techniques like renormalization, reveals a deep and complex relationship between our mathematical models and physical existence. The presence of infinity in physics is a profound mind fuck, questioning whether these infinities point to real physical phenomena or are simply artifacts of our incomplete theories, a mystery at the heart of our attempts to describe the cosmos. Let the contemplation of these cosmic and quantum extremes guide you deeper into relaxation as you fall asleep. Let's first consider the most famous and dramatic appearance of infinity in physics, the singularity. According to Einstein's theory of general relativity, a singularity is a point or region in spacetime where physical quantities like density and spacetime curvature become infinite. It's a point where the theory itself ceases to make sense, predicting nonsensical infinite values. We believe singularities exist at the heart of every black hole, where the mass of a collapsed star is crushed into an infinitely dense point. The theory also predicts that our entire observable universe began from such a singularity in the Big Bang, an initial state of infinite temperature and density. But does a physical infinity truly exist at these points? Is there a place where density is literally infinite? Most physicists think not. The appearance of a singularity in general relativity is widely interpreted as a signal that the theory itself is incomplete, that it fails under the extreme conditions of immense gravity and tiny scales found at the center of a black hole or the beginning of the universe. To truly understand these regions, we would need a theory of quantum gravity, a yet-to-be-discovered framework that successfully unifies general relativity with quantum mechanics. Such a theory, physicists hope, would resolve the singularity, replacing the infinite values with finite, albeit extreme ones. In this view, the singularity is not a physical object, but a mathematical artifact of an incomplete theory, a placeholder for a deeper understanding we have not yet attained. Nonetheless, the concept of a point of infinite density fundamentally questions our understanding of space, time, and matter at their limits. Now let's turn to another domain where infinity caused immense problems: quantum field theory, QFT. QFT is the framework that combines quantum mechanics with special relativity to describe the behavior of elementary particles and forces. When physicists in the mid-20th century tried to use QFT to calculate the interactions between particles, like an electron interacting with its own electromagnetic field, their equations kept producing nonsensical, infinite results. For example, the calculated self-energy of an electron, due to its interaction with the virtual particles constantly popping in and out of existence around it, came out as infinite. An electron's charge and mass also seemed to become infinite when calculated this way. These infinities threaten to render the entire theory useless. A theory that predicts infinite values for measurable quantities is clearly flawed. This crisis led to the development of one of the most powerful, successful, and philosophically puzzling techniques in modern physics: renormalization. In essence, renormalization is a systematic procedure for taming these infinities. Physicists realized that the bare mass or charge of a particle in their equations was just a theoretical construct, not the value we actually measure in experiments. The measured value is the bare value plus the effects of all these infinite interactions with its own surrounding field. The ingenious trick of renormalization was to posit that the bare value itself is also infinite, but in a negative way that perfectly cancels out the problematic positive infinity arising from the self-interactions, leaving behind the finite, sensible value that we actually observe in experiments. This process can be visualized as sweeping the infinities under the rug. The procedure involves introducing a cutoff to temporarily cap the infinite calculations, manipulating the equations, and then showing that as the cutoff is removed, taken to infinity, the problematic terms can be systematically absorbed into the definitions of a few physical parameters, like mass and charge, that are then set to their experimentally measured values. The resulting renormalized theory is then free of infinities and makes astonishingly accurate predictions, in the case of quantum electrodynamics, to a precision equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. But the success of renormalization raises its own deep philosophical questions, creating its own mind fuck. Is it just a mathematical trick? A clever sleight of hand that works but lacks deep physical justification? Or is it revealing something profound about the nature of reality? Does it suggest that our concepts of point particles or continuous spacetime break down at very small scales, and that the infinities arise from applying these concepts beyond their domain of validity? Some physicists like Paul Dirac were deeply troubled by renormalization, seeing it as an ugly feature that swept a fundamental problem under the rug. Others, influenced by the work of Kenneth Wilson, view it as a profound insight into how physical theories operate at different scales. They argue that the effective laws of physics we observe depend on the energy scale at which we are probing, and renormalization is the mathematical tool that describes how these effective laws change as we move from one scale to another. In this view, the infinities are artifacts of trying to extrapolate a theory valid at one scale to all scales, up to infinite energy. The very presence of infinity in physics, whether as a singularity in cosmology or a divergence in quantum calculations, acts as a signpost pointing towards the limits of our current knowledge. It tells us precisely where our theories fail and where new physics must lie. The ongoing quest for a theory of quantum gravity is, in large part, an attempt to build a framework that is free of these problematic infinities from the outset. As you continue to fall asleep, contemplate the dual nature of infinity in physics. On one hand, the singularity at the heart of a black hole or the beginning of time, a point of infinite density where our laws of existence break down. On the other, the infinite values appearing in quantum calculations, tamed by the ingenious, almost magical procedure of renormalization. Let the paradox of these infinities, both as indicators of our ignorance and as elements within our most successful theories, wash over you. Recognize the profound mystery that lies at the extreme scales of reality, the places where our mathematical models either collapse or require strange and powerful interventions. Find deep relaxation in acknowledging the vast frontiers of physics yet to be explored, resting peacefully within the grand, unfinished symphony of our quest to understand the infinite cosmos. Fractals and infinite detail. Let us now explore a form of infinity that is not about endless extension, but about endless complexity contained within a finite space. This is the realm of fractals, intricate, mesmerizing geometric shapes whose patterns repeat at progressively smaller scales, revealing infinite detail no matter how closely you zoom in. A coastline, a snowflake, a fern, a bolt of lightning, nature itself is rich with these fractal-like patterns. In mathematics, objects like the Mandelbrot set or the Koch snowflake are perfect, idealized fractals. They present a profound mind-bending concept. A shape with a finite area can possess an infinitely long perimeter. How can an endless line fit within a bounded space? Fractals challenge our intuitive Euclidean understanding of dimension and measurement, questioning the relationship between simplicity and complexity, and revealing how infinite detail can be generated from very simple rules. Contemplating the self-similar, endlessly unfolding nature of fractals can be a deeply calming and mesmerizing way to fall asleep. The core characteristic of a fractal is self-similarity. This means that a small part of the shape, when magnified, looks similar or even identical to the whole shape. This property repeats at every level of magnification, endlessly. Let's visualize the construction of a classic fractal, the Koch snowflake, to understand this. We begin with a simple shape, an equilateral triangle. Now, we apply a simple rule to the middle third of each of its three sides. We replace that middle third with two sides of a new, smaller equilateral triangle pointing outwards. We now have a six-pointed star shape. What happens if we apply the exact same rule again to every single one of the now 12 smaller straight-line segments? We add more, even smaller, triangular bumps. We repeat this process again and again infinitely. At each step, we are adding more line segments so the perimeter, the length of the boundary, increases. Since we repeat the process an infinite number of times, the length of the perimeter becomes infinite. Yet, the entire shape always remains contained within a finite, easily definable area on the page. It never expands to fill the whole plane. This is the paradox, a finite area bounded by an infinitely long line. Our intuition, accustomed to simple shapes where a larger perimeter means a larger area, breaks down. The fractal's boundary is so intricately crinkled and convoluted that its length becomes limitless. This mind-bending concept forces us to reconsider what we mean by length and dimension. Indeed, fractals often possess what is called a fractal dimension, a number that is not a whole integer like 1, 2, or 3. A line has one dimension, a square has two, a cube has three. But a fractal shape like the Koch curve has a dimension of about 1.26. It is more than a simple one-dimensional line as it starts to fill up space with its infinite crinkles, but it is less than a two-dimensional area. This fractional dimension mathematically captures the shape's complexity and its space-filling properties, questioning our simple integer-based view of dimensionality. Perhaps the most famous fractal is the Mandelbrot set. It is generated by a surprisingly simple iterative equation applied to complex numbers. The resulting shape is an object of breathtaking, seemingly infinite complexity. Zooming into its boundary reveals an endless, ever-changing landscape of intricate spirals, filaments, and miniature copies of the main shape. The complexity is not random. It is the deterministic result of a simple mathematical rule, yet its detail is inexhaustible. Exploring the Mandelbrot set feels like exploring an entire universe of form, all generated from a single equation. It demonstrates how immense complexity can emerge from profound simplicity, a theme we explored in the enigma of emergence. The implications of fractals extend far beyond beautiful mathematical art. They provide powerful models for describing many natural phenomena that are irregular and complex, things that traditional Euclidean geometry struggles with. The branching of trees and rivers, the structure of lungs and blood vessels, the jagged patterns of coastlines and mountain ranges, the structure of clouds, the patterns of galactic clusters, all exhibit fractal-like properties. This suggests that the principles of self-similarity and iterative generation might be fundamental organizing principles in nature. The universe, it seems, uses fractal geometry to build complexity efficiently across different scales. From a philosophical perspective, fractals offer a powerful metaphor for existence itself. They suggest that profound complexity and even a form of infinity can be found not just by looking outwards to the cosmos, but by looking ever deeper inwards into any given system. They challenge the reductionist idea that understanding the smallest parts is sufficient to understand the whole, because the way those parts are organized through iterative processes can generate boundless complexity. They blur the lines between order and chaos, revealing intricate, deterministic patterns that appear organic and unpredictable. The contemplation of a fractal can be a deeply meditative experience. The endless unfolding of self-similar patterns can induce a state of flow and wonder. It's a visual representation of infinity contained within a finite boundary, a paradox that is both intellectually stimulating and aesthetically calming. It questions our assumptions about what is simple and what is complex. A simple rule generates infinite detail. An infinite boundary encloses a finite space. As you continue to relax deeply, let the image of a fractal unfold in your mind's eye. Perhaps the Koch snowflake, adding ever finer triangles to its edge. Or the Mandelbrot set, a universe of detail waiting within its boundary. Follow a spiral down, ever smaller, finding the same shapes repeating, yet always new. Let this concept of infinite detail within a finite space gently dissolve any rigid notions of size and boundary. Appreciate the profound beauty that can emerge from the simple, repeated application of a rule. Find deep relaxation in the intricate, endless yet contained complexity of these mathematical wonders, resting peacefully within the mesmerizing, infinite patterns generated by pure thought. The infinite monkey theorem. Imagine a monkey, or better yet, an infinite number of monkeys, seated at an infinite number of typewriters, each one hitting keys randomly without thought or intention for an infinite amount of time. The infinite monkey theorem states that, given these conditions, one or more of these monkeys will almost surely, with a statistical probability approaching 1, eventually type out the complete, verbatim works of William Shakespeare. In fact, they would type out every book in the Library of Congress, every possible book ever written, and every possible book that could be written, along with an infinitely larger amount of unintelligible gibberish. This famous thought experiment is not really about monkeys. It's a profound illustration of the relationship between randomness, probability, and infinity. It presents a mind-bending concept, that within an infinite expanse of randomness, Any finite pattern, no matter how complex or seemingly meaningful, is not just possible but virtually inevitable. This paradox challenges our intuitions about chance, order, and meaning, questioning whether profound complexity can arise from sheer, unguided randomness, given enough opportunities. Let this idea of infinite possibility gently expand your mind as you fall asleep. To understand why this seemingly impossible outcome is considered a mathematical near-certainty, we need to think about probability. The chance of a single monkey randomly typing the first letter of Hamlet, H, assuming a simple keyboard, is small. The chance of typing Ha is much smaller. The chance of typing the entire play, a sequence of hundreds of thousands of specific characters, is so astronomically small as to be practically zero in any finite time frame. Our intuition rebels at the idea of it happening by chance. However, the theorem introduces the crucial element of infinity. With infinite time or infinite monkeys, the number of attempts becomes limitless. The probability of failing to type Hamlet on any given stretch of text is very high, but it is less than 1. When you multiply this probability of failure by itself an infinite number of times, representing infinite attempts, the overall probability of always failing approaches 0. Consequently, the probability of succeeding at least once approaches 1. In the vast, boundless ocean of infinite random characters, every finite sequence must eventually appear. The infinity of attempts completely overwhelms the improbability of any single attempt. This theorem provides a powerful intuitive handle on the nature of large numbers and infinity. It demonstrates that given enough shots, even the most improbable events become commonplace. It forces us to distinguish between what is physically practical and what is mathematically possible. No one could ever actually set up an experiment with infinite monkeys or wait for infinite time. But in the abstract realm of mathematics, the logic holds. The philosophical implications are profound and create a deep mind fuck. If any ordered, meaningful text like Hamlet can be produced by pure randomness, what does this say about the nature of meaning, creation, and intelligence? It suggests that, given a large enough possibility space, order can emerge from chaos without any guiding hand or intention. This can be interpreted in several ways. On one hand, it could be seen as a challenge to arguments from design, which often point to complex, ordered structures, like life, as evidence of an intelligent creator. The infinite monkey theorem suggests that complexity and apparent design might, in principle, arise from random processes given a vast enough cosmic context, perhaps a multiverse with infinite variations. On the other hand, the theorem also highlights what makes genuine creation so special. While a monkey might type Hamlet, it would not understand it. It would not have the intention, the emotion, the cultural context, the genius of Shakespeare. The monkey's output would be a random artifact, a sequence of characters that we recognize as meaningful. The meaning is not inherent in the random process. It is projected onto it by an intelligent observer. This suggests that meaning and creation are not just about producing a particular pattern, but about the process of intentional, conscious, and context-aware creation. The theorem, therefore, paradoxically reinforces the special nature of intelligence by showing how different it is from random generation, even when they can produce the same output pattern. This paradox also questions our place in the existence. If the universe is infinite in space or time, as some cosmological models suggest, then the theorem implies that every possible event, every possible configuration of matter, must occur somewhere, sometime, and infinitely often. This leads to mind-bending concepts like Boltzmann brains, which we may explore later. The idea that it might be more statistically likely for a fully formed conscious brain to randomly fluctuate into existence out of the chaos of deep space than for a complex, ordered universe like ours to evolve. It forces us to grapple with the potential absurdity and vastness of an infinite reality, where our own seemingly unique and precious existence could be just one of an infinite number of identical copies, some created by ordered evolution, others by sheer random chance. The infinite monkey theorem is not just about typing monkeys. It's a powerful metaphor for understanding the nature of randomness, the power of large numbers, and the emergence of order from chaos. It's a tool for thinking about probability in fields from statistical mechanics, the random motion of particles creating stable thermodynamic properties, to cryptography, the difficulty of guessing a long random password, to evolutionary biology, random mutations providing the raw material for natural selection. As you continue to relax deeply, let the image of the infinite monkeys at their infinite typewriters gently fade in and out of your awareness. Hear the endless clatter of random keys. And imagine, somewhere in that infinite chaos, the words, to be or not to be, spontaneously appearing. Contemplate the profound implication that in an endless sea of randomness, every island of order is destined to emerge. Let this concept dissolve your rigid notions of cause, creation, and meaning. Find deep relaxation not in purpose or design, but in the sheer boundless potential of infinity itself. The idea that given enough time and chance, anything that is not impossible is inevitable, resting peacefully within the vast, chaotic, and ultimately all-encompassing library of random existence. Skolem's paradox. We now venture into one of the most subtle, abstract, and genuinely mind-bending paradoxes from the foundations of mathematics, Skolem's paradox. This paradox appears to reveal a deep contradiction within modern set theory, the very language used to describe different sizes of infinity. As we saw with Cantor's diagonal argument, set theory proves that some infinite sets, like the real numbers, are uncountable. They are a larger size of infinity than the countable set of natural numbers, 1, 2, 3. The paradox, discovered by logician Thorolf Skolem, arises from a different theorem, the Lowenheim-Skolem theorem, which implies that if our standard axioms of set theory are consistent, they must have a countable model. This means there must be a way to interpret the entire universe of sets, including the supposedly uncountable ones, using only a countable number of objects. This creates the apparent contradiction. How can a countable model contain a set that the axioms within that model prove to be uncountable? How can a smaller infinity seem to hold a larger one? Skolem's paradox is not a true logical contradiction, but a profound puzzle about the relativity of mathematical concepts like set, countable, and infinity to the specific formal system or model being used. It questions the absolute nature of mathematical truth and suggests that the size of infinity might not be an absolute property, but a relative one, depending on the perspective from which it is viewed. This subtle distinction invites deep contemplation as you fall asleep. To begin to unravel this, we must touch upon the idea of a model in logic. A model is a specific mathematical structure in which the axioms of a theory are interpreted as true. Our standard axioms for set theory, usually ZFC, describe a vast universe of sets. The Lowenheim-Skolem theorem states that if these axioms have any model at all, then they must also have a model that is countable. This means we can construct a universe of sets using only a countably infinite number of surrogate sets, where all the standard axioms of set theory still hold true. Now, within this countable model, we can run the proof of Cantor's theorem. The proof still works perfectly, and within the model, it proves the existence of a set, the set of real numbers of that model, that is uncountable. Here is the paradox. We have a countable collection of objects, our model, yet one of these objects, when viewed from inside the model's own logic, is declared to be uncountable. How can a set be uncountable from the inside but countable from the outside? The resolution lies in understanding what uncountable actually means within a formal system. A set is proven to be uncountable within a model if there is no one-to-one correspondence, a bijection, within that same model that can pair its elements with the natural numbers. In our countable model, the set of real numbers is indeed one of the countably many objects. We, looking at it from the outside, can see that its elements could be listed out because the entire model is countable. However, the listing function, the specific one-to-one correspondence needed to prove its countability from the outside, does not exist as a set within the countable model itself. The model is missing the very function that would reveal the uncountability of its real numbers to be only an internal truth. Think of it like this. Imagine a hotel with only a countable number of rooms, like Hilbert's hotel. The hotel's logbook, which lists all its officially recognized pairing functions, is also just one of the items within the hotel. We can show that, from outside the hotel, we could create a list pairing every guest with a room. But the paradox is like saying the hotel's own logbook contains a proof that some group of guests is unlistable, because the specific list we created from the outside isn't written down in their official logbook. The property of being uncountable is relative to the resources available within the system. This has profound philosophical implications for the nature of mathematical reality. It suggests that the concept of size for an infinite set is not an absolute, God's eye view property, but is relative to the set-theoretic universe, the model, one is working within. A set that is uncountable in one model could potentially be countable in a larger model that contains the necessary pairing function. This is known as the relativity of set-theoretic concepts. It challenges mathematical Platonism's view of a single, absolute universe of sets with fixed properties. Instead, it hints at a multiverse of possible mathematical realities, where properties like cardinality can be relative. This mindfuck questions the very objectivity we attribute to mathematics. We think of the set of all real numbers as a single definite entity with a fixed, uncountable size. Skolem's paradox suggests that what we can prove about such entities depends on the axiomatic framework we assume, and that there can be different, non-isomorphic universes that all satisfy those same axioms, yet disagree on fundamental properties like cardinality. It strikes at our confidence in language's ability to perfectly pin down unique mathematical structures. Our axioms, it seems, are not powerful enough to describe a single, unique set-theoretic universe. They allow for multiple interpretations, some of which seem deeply paradoxical from an external perspective. The paradox is not a contradiction in mathematics, but a surprising result about the relationship between formal theories and their models. It shows a gap between syntax, the formal proofs within a system, and semantics, the interpretation of the system in a model. The statement, the set of real numbers is uncountable, is provable, but its truth or meaning can be relative to the model. As you continue your journey towards sleep, let the strange relativity of Skolem's paradox gently expand your mind. Contemplate a countable universe of sets that contains within it a set it believes to be uncountable. A smaller infinity holding what it perceives to be a larger one. Recognize that the concepts of size and infinity might be more context-dependent, more relative, than we ever imagined. Let this paradox dissolve any notion of a single, absolute mathematical reality. Find deep relaxation in the idea of a multiverse of mathematical possibilities, where truth itself can be a matter of perspective, resting peacefully within the subtle, shifting, and deeply enigmatic foundations of logic and infinity. The nature of zero and its relation to infinity. In our journey through the vast and paradoxical landscapes of the infinite, we have explored the immensely large, the endlessly divisible, and the eternally recurring. Now, let us turn our focus to the other extreme of the number line, to a concept so fundamental yet so historically elusive that its acceptance revolutionized mathematics. The number 0, 0. Far from being simple nothingness, zero is a concept laden with profound philosophical weight and mathematical power. It acts as a placeholder, a number in its own right, and a gateway to some of the most perplexing ideas in all of thought. Its relationship with infinity is particularly intimate and mysterious. What happens when these two concepts, the embodiment of nothing and the embodiment of everything, interact? The attempt to perform division by zero serves as a focal point for this mystery, revealing a deep schism in mathematical logic where the rules seem to break down completely, leading to contradictions or undefined states. The nature of zero and its paradoxical dance with infinity is a subtle but potent mind fuck, questioning the completeness of arithmetic and the very meaning of fundamental operations. Let this contemplation of nothingness and its relation to everything guide you into a state of profound, quiet relaxation as you fall asleep. For most of ancient history, Western mathematics had no concept of zero as a number. The Greeks, with their focus on geometry and tangible magnitudes, had no place for a symbol representing nothing. It was primarily through the contributions of Indian mathematicians, like Brahmagupta in the 7th century, that zero began to be treated not just as a placeholder, as the Babylonians and Mayans had used it, but as a genuine number with which one could perform arithmetic. They defined rules for addition, subtraction, and multiplication involving zero. But when it came to division, a deep problem emerged. Let's consider division by zero from a simple, intuitive perspective. Division can be thought of as the inverse of multiplication. The statement 10 divided by 2 equals 5 is true because 5 multiplied by 2 equals 10. Now, let's try to calculate 10 divided by 0. We are looking for a number x, such that x multiplied by 0 equals 10. But we know that any number multiplied by 0 is 0. There is no number that, when multiplied by 0, can give us 10. The equation has no solution. Therefore, from this perspective, division by 0 is undefined. It's not a number, it's a question with no possible answer within the standard rules of arithmetic. But our intuition often pushes us towards infinity. We notice a pattern. As the divisor gets smaller and smaller, the result gets larger and larger. 10 divided by 1 is 10. 10 divided by 0.1 is 100. 10 divided by 0.001 is 1000. As the divisor approaches zero, the result seems to race towards infinity. This leads many to intuitively conclude that 10 divided by 0 equals infinity. This very intuition hints at the deep, inverse relationship between the infinitely small and the infinitely large. However, treating division by 0 equals infinity as a simple fact creates immediate and disastrous paradoxes within our mathematical system. If we allow this, we can quickly prove that all numbers are equal. For example, we know that 0 multiplied by 1 is 0, and 0 multiplied by 2 is 0. So, we can say that 0 times 1 is equal to 0 asterisk 2. If we were allowed to divide both sides of this equation by 0, we could cancel out the zeros, leaving us with the absurd conclusion that 1 is equal to 2. To preserve the consistency of all of arithmetic, standard mathematics forbids division by 0 entirely. It is left as an undefined operation, a kind of logical void in the system. The path towards infinity suggested by the pattern is blocked by a wall of logical necessity to prevent the entire structure from collapsing into contradiction. This is where the mindfuck deepens. We have a clear intuitive and limit-based connection between 0 and infinity, yet our formal systems must forbid this connection to remain consistent. This tension reveals the difference between the potential approach of limits and the actual operation of division. In calculus, we can talk about the limit of a function as its denominator approaches 0, and this limit can indeed be positive or negative infinity. This is a statement about the behavior of the function near that point. But this is not the same as defining the value of the function at that point. The operation itself remains undefined. More advanced mathematical structures have been created to try and formally incorporate this relationship. In projective geometry, a point at infinity is added to the real number line, and the line is conceptually bent into a circle. In this system, one can sometimes define 1/0 as this single point at infinity. Another system, the Riemann sphere, used in complex analysis, adds a single point at infinity to the complex plane, providing a context where division by 0 can be given a meaningful interpretation. However, these are specialized geometric systems. To make them work, you have to sacrifice some of the standard rules of arithmetic. For example, in a system with a single point at infinity, you lose the sense of order. You can't say that positive infinity is different from negative infinity. You gain a way to handle division by 0, but you lose other properties. There is no system that allows for division by 0 while preserving all the familiar rules of algebra. It's a fundamental trade-off. The nature of 0 itself is philosophically profound. Is it the representation of nothingness? The boundary between positive and negative numbers? An identity element for addition? It is all of these things. Its dual role as both a number and a symbol for emptiness is part of its power and mystery. Its relationship with infinity is one of profound duality and inversion. They are like two sides of a coin, two poles of a magnet. They are the conceptual limits of our number system, the points where our familiar intuitions about quantity break down. Contemplating division by 0 is not just a mathematical exercise. It's a philosophical exploration of the limits of our logical systems. It questions whether our systems of reason can be complete and handle all conceivable operations without either breaking down or requiring modification. The fact that such a simple, intuitive question, what is a number divided by nothing? Leads to such deep problems reveals the delicate and carefully constructed nature of mathematics. It shows that the rules are not arbitrary, but are carefully chosen to maintain consistency and avoid the abyss of paradox. This psychology mystery of why we are so drawn to the idea of 1/0 equals infinity reveals our mind's preference for patterns and continuity over abrupt, undefined breaks. We want the pattern of the approaching limit to hold true at the limit point itself. The mathematical refusal to allow this is a testament to the supremacy of logical consistency over intuitive appeal. It's a reminder that the world of formal thought operates by its own strict rules, even when those rules create boundaries that feel unnatural to us. As you continue to fall asleep, allow your mind to rest at the profound boundary point of 0. See it as the origin, the void, the point of perfect balance. Now, feel the conceptual pull as you imagine dividing by numbers that get ever closer to it, the result rocketing away towards the boundless expanse of infinity. Contemplate the paradox, an intuitive connection that must be formally forbidden to prevent logical chaos. Let the undefined nature of division by 0 be a source of peace, a recognition that some questions are left unanswered not out of ignorance, but out of logical necessity. It is a quiet guardrail protecting the coherence of the entire mathematical world. find deep relaxation in this conceptual void, this point of undefinedness, a place where the rules of finite existence gracefully bow out, resting peacefully at the still, silent, and infinitely mysterious center of the number line. The paradox of self-reference involving infinity. We now return to the treacherous and fascinating domain where language and mathematics attempt to describe themselves, a domain where infinity often lurks in the background, generating profound paradoxes. We will explore a family of semantic paradoxes, closely related to Russell's and Grelling's paradoxes but with a unique flavor, that arise from the attempt to define specific numbers using finite descriptions. These are paradoxes like Richard's paradox and Berry's paradox. They create a deep mind fuck by using the finite tool of human language to talk about the infinite set of numbers, leading to self-referential loops that seem to define a number that, by its very definition, cannot be defined. These puzzles question the power and consistency of language to fully capture the vastness of mathematical reality, highlighting a fundamental mismatch between our finite descriptive abilities and the infinite objects we seek to describe. Let this exploration of language folding back upon itself amidst infinity gently guide you deeper into relaxation as you fall asleep. Let's begin with Berry's paradox, which is perhaps the most intuitively graspable. It focuses on the concept of definability. Consider the phrase, the smallest positive integer not definable in fewer than 20 syllables. Let's analyze this phrase carefully. It seems to point to a specific, unique number. There are only a finite number of possible phrases with fewer than 20 syllables. Therefore, there can only be a finite number of positive integers that can be defined by such phrases. However, the set of positive integers is infinite. This means there must be integers that cannot be defined in fewer than 20 syllables. Since any non-empty set of positive integers has a smallest member, there must indeed be a smallest positive integer not definable in fewer than 20 syllables. The phrase seems to successfully and uniquely identify a specific number. But here is the paradox. Let's count the syllables in the defining phrase itself. The smallest positive integer not definably in fewer than 20 syllables. That phrase has 19 syllables. So, the phrase which supposedly defines this number is itself a phrase of fewer than 20 syllables. This means we have just defined the number using a phrase of 19 syllables. But the number was defined as the one that cannot be defined in fewer than 20 syllables. We have created a contradiction. The number is defined as being undefinable by the very kind of phrase that defines it. If the phrase defines a number, then that number is, by definition, definable in 19 syllables, which contradicts its own definition. If the phrase doesn't define a number, then what are we even talking about? The attempt at self-reference within the context of definability and the implicit use of the infinite set of integers creates an inescapable logical knot. Richard's paradox, formulated by Jules Richard in 1905, is a more formal, mathematical version of the same underlying idea. It uses a method similar to Cantor's diagonal argument, but applies it to the set of definable real numbers. The argument goes like this. First, consider all possible finite definitions of real numbers that can be stated in the English language, or any formal language. Since there are a finite number of symbols and we are only considering finite length definitions, we can in principle arrange all these definitions in an ordered list, e.g., alphabetically and by length. This means that the set of all definable real numbers is countably infinite. We can list them out, 1, 2, 3 and so on. Now, Richard invites us to use a diagonal procedure, much like Cantor's, to construct a new real number. We will create a number, let's call it r, such that its nth decimal place is different from the nth decimal place of the nth number in our list of all definable real numbers. For example, we add 1 to the digit, wrapping around from 9 to 0. This procedure clearly and unambiguously defines the new number r. However, by its very construction, this number r cannot be on our original list. It differs from the first number in the first decimal place, the second number in the second decimal place, and so on. So, we have a contradiction. We have just provided a finite English language definition for the number r. Therefore, r is a definable real number and should be somewhere on our complete list of all definable real numbers. But we have also just proven by its very construction that r cannot be on that list. This is the paradox. The resolution to these semantic paradoxes, much like Russell's paradox, lies in recognizing the dangers of unrestricted self-reference and the ambiguity of concepts like definable. The key issue is that the definition of the paradoxical number, in both Berry's and Richard's case, relies on quantifying over a totality, all definitions, to which the definition itself belongs. When Richard defines his number r, his definition is the number whose nth digit differs from the nth digit of the nth number in the list of all definable numbers. To understand this definition, you must first have the entire list of all definable numbers already established. But the definition of r is itself one of those definitions, so it should be on the list. The definition becomes circular and ill-formed. Logicians resolve this by introducing a hierarchy of languages or types. A definition formulated in a meta-language, a language used to talk about the object language, cannot be considered part of the object language itself. Richard's definition of r is a metalinguistic statement about the list of object language definitions, and therefore r is not on that original list, and there is no contradiction. However, the philosophical mindfuck remains. These paradoxes demonstrate that our natural language is not so neatly stratified. It inherently allows for this kind of self-application that leads to contradiction. They reveal a fundamental tension between the expressive power of language, its ability to describe anything, including its own properties like definability, and the requirements of logical consistency. They question whether there can be a single, all-encompassing language or formal system capable of describing all of mathematical reality without generating such paradoxes. It hints that the universe of numbers and definitions might be structured in layers, and any attempt to describe the whole system from within the system itself is fraught with peril. These paradoxes are not mere curiosities. They lie at the heart of foundational crises in mathematics and led to profound insights, including Gödel's incompleteness theorems. They force us to accept that our tools for describing existence, particularly when dealing with infinity and self-reference, have inherent limitations. The very act of naming and defining, when turned upon itself, can create logical voids. As you continue your journey towards sleep, let these linguistic loops gently spin in your mind. The number defined as undefinable. The list that cannot contain a number constructed from the list itself. Feel the way language and logic can tie themselves into knots when they try to grasp their own tails. Find deep relaxation not in resolving the contradiction, but in appreciating the profound mystery it reveals about the limits of definition and the slippery nature of self-reference. Acknowledge that our understanding is built with tools that are themselves part of the universe they seek to describe, resting peacefully within the elegant, self-referential, and ultimately paradoxical nature of thought itself. Geometric series and convergence. We have spent much of our journey tonight grappling with infinity as a source of paradox, impossibility, and unsettling vastness. Zeno's paradoxes used infinite division to question motion. Hilbert's hotel used infinite rooms to defy our sense of capacity. Now, let us turn to a concept that offers a different, almost magical perspective on infinity, a perspective of containment and peace. This is the concept of geometric series and convergence. It addresses the question, what happens when you add up an infinite number of numbers? Our intuition screams that the sum must also be infinite. Yet, mathematics reveals the profound and beautiful truth that, under certain conditions, an infinite sum can add up to a perfectly finite, specific result. This idea that an endless process can yield a bounded and definite outcome is not just a mathematical curiosity, it is the very key that resolves Zeno's paradoxes and underpins much of calculus and our modern understanding of the continuous world. It's a gentle mind fuck that domesticates infinity, showing how endlessness can be contained, and it questions our intuitive link between infinite process and infinite outcome, inviting deep relaxation through the contemplation of infinite parts forming a finite whole. Let's visualize this with a simple example, echoing Zeno's dichotomy paradox. Imagine walking towards a wall that is 1 meter away. First, you walk half the distance, 1/2 meter. Then you walk half of the remaining distance, which is 1/4 of a meter. Then half of what's left, 1/8 of a meter, then 1/16, and so on. You continue this process forever, always walking half the remaining distance. You are taking an infinite number of steps. The total distance you have walked is the sum of this infinite geometric series. 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and so on, forever. Our initial paradox-prone intuition might say that since you are adding numbers forever, the sum must grow infinitely large. But let's look closer. With each step, the distance you add becomes progressively, exponentially smaller. You get closer and closer to the wall, but you never pass it. The wall itself represents a boundary, a limit. The mathematical concept of convergence gives us a precise way to understand this. A series converges if its sequence of partial sums, the sum after one term, then two terms, then three, etc., approaches a specific finite limit as the number of terms goes to infinity. In the case of our series, the sum gets closer and closer to exactly 1. It never exceeds it, but it fully fills up the distance. The infinite sum of 1/2 plus 1/4 plus 1/8 plus has a perfectly finite result, 1. This resolution is profoundly powerful. It tells us that Zeno's runner can complete the infinite number of tasks required to cross a distance because the sum of the time taken for each of those infinitely decreasing tasks also converges to a finite amount of time. The infinite process doesn't require infinite duration. This concept of a convergent series is one of the cornerstones of calculus, the mathematical language of change. It allows us to handle continuous motion, to calculate the areas of curved shapes, and to understand rates of change by breaking them down into an infinite number of infinitesimally small parts and then summing them back up. The idea of convergence provides a beautiful bridge between the discrete and the continuous, between the finite and the infinite. It shows how a smooth, continuous line can be thought of as being composed of an infinite number of points, yet still have a finite length. It shows how a finite area can be calculated by summing an infinite number of infinitesimally thin slices. It retains the idea of infinite divisibility that so troubled the ancient Greeks but provides a rigorous framework for showing how these infinite divisions can resolve into finite, manageable quantities. But the mind-bending quality persists. How does an endless addition result in a non-endless number? The conceptual leap is from the process, which is infinite, to the result, which is finite. Our minds struggle to hold both ideas at once. We are accustomed to finite processes yielding finite results. The idea of an infinite process yielding a finite one feels like a kind of mathematical alchemy. It questions the very nature of what a sum is. It is not just about repeatedly adding, but about approaching a limit, a value that the sum gets arbitrarily close to and never surpasses. Consider another famous example, the number 0.999, where the nines repeat forever. This is an infinite geometric series in disguise. 9/10 plus 9/100 plus 9/1000 plus. Our intuition might tell us that this number is always just a little bit less than 1. But mathematically, 0.999 repeating is exactly equal to 1. There is no number you can squeeze between 0.999 and 1. The limit of that infinite sum is precisely 1. This result often feels deeply counterintuitive, a testament to how our finite minds grapple with the concept of an infinitely repeating decimal. It's a clear case where formal mathematical proof leads to a conclusion that our intuition resists. The concept of convergence doesn't just resolve paradoxes. It reveals a profound structural truth about our mathematical description of reality. It suggests that the continuous nature of space and time as we model them is built upon this principle of infinite sums having finite results. It's the silent mathematical engine running beneath our understanding of everything from planetary orbits to the flow of heat. It's infinity not as a terrifying, expanding void, but as an intricate, fine-grained texture that constitutes the finite world we experience. As you continue to fall asleep, let the idea of convergence bring a sense of calm and containment to the concept of infinity. Picture an endless series of steps, each one smaller than the last, peacefully and perfectly adding up to a finite journey, an infinite sum with a finite result. Let go of the intuitive fear that infinite process must mean infinite outcome. Appreciate the elegance of the limit, the boundary that an endless process can approach but never cross. Find deep relaxation in this mind-bending math concept, where the infinite is tamed, contained, and made coherent, a paradox that resolves into a profound and beautiful order, resting peacefully within the calm certainty of a finished sum composed of endless parts. The idea of infinitesimals. Continuing our exploration of infinity contained within the finite, we now turn to a concept that lies at the very foundation of calculus and our entire mathematical understanding of change, the infinitesimal. An infinitesimal is a strange and elusive quantity, a number imagined to be so small that it is greater than 0, yet smaller than any positive real number you can name. It is an infinitely small quantity, a ghost of a number that bridges the gap between 0 and the finite. For centuries, the idea of infinitesimals was both incredibly useful and deeply paradoxical, leading to the development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz, but also prompting fierce criticism for its apparent lack of logical rigor. Are infinitesimals real mathematical objects, or are they a convenient, if logically dubious, fiction? The story of the infinitesimal is a mind-bending journey into the foundations of mathematics, questioning the nature of continuity, the meaning of zero, and how we can possibly reason about quantities that are perpetually vanishing yet never quite gone. Let this subtle, almost nothing of a concept guide your mind into a state of deep relaxation as you fall asleep. The invention of calculus was motivated by the need to solve problems involving continuous change, the speed of a falling object at a single instant, the slope of a curve at a single point, the area under a curve. To do this, Newton and Leibniz imagined breaking down continuous motion and shapes into an infinite number of infinitely small pieces, or infinitesimals. To find the instantaneous velocity of an object, for example, they considered the change in its position over an infinitesimally small interval of time, dt. To find the area under a curve, they imagined summing the areas of an infinite number of infinitesimally thin rectangles. This method was incredibly powerful and produced correct results, unlocking a revolution in physics and engineering. However, the logical status of the infinitesimal itself was highly problematic. At some points in a calculation, infinitesimals were treated as if they were not zero. For example, you could divide by dt. Yet, at the end of the calculation they were often discarded as if they were zero, to arrive at the final finite answer. This practice led to sharp criticism. The philosopher Bishop Berkeley famously derided infinitesimals as the ghosts of departed quantities, questioning how a quantity could be non-zero for one part of a proof and zero for another without creating a contradiction. For nearly 2 centuries, calculus rested on these shaky foundational grounds. It worked beautifully, but nobody could quite explain why in a way that was logically airtight. The method was a magnificent, useful paradox. The solution to this problem came in the 19th century with the work of mathematicians like Cauchy and Weierstrass, who reformulated the foundations of calculus using the concept of limits, which we touched upon in our discussion of convergence series. Instead of talking about infinitely small quantities, the limit-based approach talks about a process of getting arbitrarily close to a certain value. For instance, to find the slope of a curve at a point, we no longer look at an infinitesimal interval, but at the limit of the slopes of lines through progressively smaller finite intervals as the size of the interval approaches zero. This epsilon-delta definition of a limit successfully banished the paradoxical infinitesimals from mainstream mathematics, placing calculus on what was considered a much more rigorous logical footing. For over a century, the infinitesimal was largely relegated to the status of a useful but heuristic fiction. However, the story has a mind-bending twist. In the 20th century, a logician named Abraham Robinson developed a new branch of mathematics called non-standard analysis. Robinson rigorously proved that it is possible to create a consistent mathematical system that includes genuine infinitesimal and infinite numbers. He constructed the hyperreal number system, an extension of the real numbers that contains quantities that are infinitely small, infinitesimals, and infinitely large. Within this system, the intuitive methods of Newton and Leibniz could be fully and logically justified. The ghosts of departed quantities were given a new, logically sound lease on life. This development reveals a profound truth about mathematics. There can be multiple, different, yet internally consistent ways to build a foundation for the same set of powerful ideas. The rejection of infinitesimals wasn't a final truth, but a choice of one particular foundational path over another. The idea of infinitesimals continues to question our most fundamental intuitions about number and continuity. What does it even mean for something to be smaller than any real number but still not zero? It challenges the Archimedean property of the real number line, which states that for any 2 positive numbers, you can add one to itself enough times to exceed the other. Something not true for an infinitesimal. It suggests that the number line might have a far more intricate, layered structure than we typically imagine, with an entire cloud of infinitesimal values clustered around every real number. This mystery pushes us to consider the relationship between mathematical constructs and physical reality. Does the success of limit-based calculus mean the physical world is continuous in the way the real numbers describe? Or does the logical coherence of non-standard analysis with infinitesimals suggest a different possible structure for spacetime? Or, perhaps, are both just different powerful languages for modeling a reality whose ultimate nature, whether continuous or discrete, remains unknown? The debate over the true foundations of calculus reveals that even in our most precise science, choices of conceptual framework can lead to different, equally powerful ways of seeing the world. As you continue to fall asleep, imagine a line stretching before you. Between any 2 points you can name, no matter how close, there lies another. Now imagine quantities so small they are squeezed into the very space around a point like 0, closer than any finite distance, yet still distinct from it. These are the infinitesimals, the ghosts of quantities that powered a scientific revolution. Contemplate the paradox of their existence, for centuries logically suspect yet practically brilliant, then banished by limits, only to be resurrected by modern logic. Let this story of shifting foundations dissolve any notion of a single absolute path to mathematical truth. Find deep relaxation in the subtle, almost nothingness of the infinitesimal, a concept that bridges the gap between the discrete and the continuous, the static and the dynamic, resting peacefully within the profound foundational mystery of how we measure change in a constantly flowing existence. Philosophical implications of infinity. Throughout our journey tonight, we have explored a series of mathematical and logical paradoxes arising from the concept of infinity. We have seen it defy our notions of size, motion, space, and proof. Now, as we draw our exploration towards a close, let us zoom out and contemplate the broader philosophical implications of infinity. What does the existence of this concept, whether as a mathematical reality or a product of pure thought, mean for our understanding of the universe, our place within it, and the limits of human knowledge? The idea of infinity is not just a tool for calculation. It is a profound philosophical catalyst, forcing us to confront the boundaries of our intuition, the nature of reality, and the scope of our own minds. It poses some of the deepest questions about existence, offering a unique pathway to humility, wonder, and a form of deep relaxation born from contemplating the boundless. Let us drift together through these vast implications as we prepare for sleep. One of a central philosophical tension ignited by infinity is between the potential and the actual. For much of history, following Aristotle, philosophers and mathematicians were comfortable only with the idea of potential infinity. This is infinity as an endless process. You can always count one more number, you can always divide a line segment again. The process never terminates, but you never have to confront a completed, existing infinite set. Actual infinity, the idea of an infinite set existing as a single, completed totality, like the set of all natural numbers or all points on a line, was considered paradoxical and logically suspect. It was George Cantor's work that forced mathematics to take actual infinity seriously, leading to many of the mind-bending concepts we've explored. This philosophical divide remains. Does the physical universe contain actual infinities, e.g., is space infinitely large or infinitely divisible? Or are all infinities in the physical world merely potential? The answer profoundly shapes our cosmological models and our understanding of physical reality. The concept of infinity also has deep implications for cosmology. Is the universe spatially infinite, stretching on forever? If so, the infinite monkey theorem suggests that in that infinite space, every possible configuration of matter must exist somewhere, meaning there are infinite copies of you, me, and our entire observable universe out there in the cosmic darkness. This is the staggering idea of the quilted multiverse, or patchwork universe. Alternatively, is the universe finite but unbounded like the surface of a sphere? Or does it have an edge? Similarly, is the universe temporally infinite, having existed forever or destined to exist forever, perhaps through cycles of big bangs and big crunches? Or did time itself have a beginning and will it have an end? Our models of cosmic origins and ultimate fate are deeply entangled with how we treat the concept of infinity. The singularities predicted by general relativity represent points where physical theory grapples with mathematical infinity, hinting at the limits of our current understanding. In the realm of theology and metaphysics, infinity has always been a key attribute of the divine. God is often conceived as being infinite in power, omnipotent, knowledge, omniscient, and goodness, omnibenevolent. Philosophical debates have long explored whether a single being can coherently possess these infinite attributes, and how a truly infinite being can interact with a finite world. The concept of mathematical infinity, with its different sizes and strange properties, has provided new language and new puzzles for these ancient theological discussions. Does the existence of transfinite numbers tell us anything about the nature of a divine mind? Or are they entirely separate concepts? The relationship between the mathematical infinite and the metaphysical infinite remains a source of profound philosophical speculation. Infinity also forces us to confront the limits of human knowledge and intuition. As we've seen repeatedly, our intuition, honed in a finite world, consistently fails us when trying to grasp the infinite. The whole can be the same size as its part, Galileo's paradox. An infinite sum can be finite, convergence. A finite area can have an infinite boundary, fractals. These results are not just quirks, they are fundamental truths of infinite mathematics. This demonstrates that pure reason and formal logic can lead us to realities that are profoundly counterintuitive. It questions the reliability of common sense as a guide to ultimate truth and underscores the necessity of rigorous, formal systems to navigate these non-intuitive realms. It fosters a deep intellectual humility, a recognition that our minds may not be naturally equipped to comprehend the full scope of reality's potential structure. Furthermore, the contemplation of infinity can have a profound psychological and existential impact. On one hand, it can evoke a sense of awe, wonder, and transcendence, what has been called the oceanic feeling. Contemplating the infinite cosmos or the endless complexity of a fractal can make our personal concerns seem small and insignificant, leading to a sense of peace and connection to something larger than ourselves. It can be a source of artistic and spiritual inspiration. On the other hand, it can also evoke feelings of dread, insignificance, and vertigo. The thought of infinite time can make our finite lives seem meaningless. The thought of infinite space can make us feel cosmically alone and adrift. Our emotional response to infinity is itself paradoxical, capable of inspiring both profound solace and profound anxiety. The very fact that our finite minds can conceive of, reason about, and even prove theorems about infinity is a mystery in itself. How can a finite system, the human brain, generate and manipulate a concept that so radically transcends its own limitations? This is perhaps the ultimate mindfuck of infinity, its presence as a coherent, workable concept within our own finite thoughts. As you finally let go and drift into sleep, let the vast, paradoxical nature of infinity be the final thought that dissolves. See it as the endless expanse of space, the eternal passage of time, the infinitesimal divisions in a single moment, the inexhaustible detail in a single pattern. Acknowledge it as the ultimate limit concept that defines the boundaries of our understanding, and yet is a product of it. Let go of the need to fully grasp it. Find deep relaxation in simply floating within the idea of the boundless, the endless, the infinite, resting peacefully as a finite being within the contemplation of an infinite existence. Visualizing infinity. Our final contemplation on this journey is not a paradox in the logical sense, but a reflection on the very act of trying to see the unseeable, to conceptualize the inconceivable. We have explored the logic and the implications of infinity, but how do we bridge the gap between these abstract ideas and our sensory, intuitive minds? This is the challenge of visualizing infinity. Through the beauty of mathematical art, particularly fractals, and the power of imaginative thought experiments, the human mind attempts to create tangible metaphors and windows into the boundless. This final segment is an invitation to engage this imaginative faculty, to see how art and thought can create stepping stones into the abyss of the infinite, offering a pathway to deep relaxation not through logical resolution, but through aesthetic wonder and contemplative practice. The mind-bending task of picturing the endless provides a final, peaceful gateway to sleep. Let us begin with mathematical art and specifically the fractals we touched upon earlier. A fractal, with its property of infinite self-similarity, is perhaps our most powerful tool for visualizing a certain kind of infinity, the infinity of detail. As you imagine a shape like the Mandelbrot set, picture yourself at its boundary. You are looking at an incredibly intricate coastline, separating the points inside the set from those outside. Now, zoom in on a small section of that coastline. The complexity does not simplify. Instead, new equally intricate patterns emerge, spirals, filaments, miniature copies of the whole set, often called mesas. Zoom in again on a tiny part of one of these new spirals. Again, no simplification. More detail, more structure, more beauty unfolds. This process can continue forever. The act of mentally zooming into a fractal is a direct, visual metaphor for an infinite process. You are traveling endlessly deeper into a landscape of inexhaustible complexity, all contained within a finite boundary. This visual journey questions our standard notion of detail. It suggests a world where the closer you look, the more there is to see ad infinitum. It is a visual representation of a convergent process with an infinite number of steps. Allow your mind's eye to gently perform this zoom, feeling the sense of wonder as endless detail unfolds from a simple mathematical rule. Another powerful visualization comes from the art of M.C. Escher. His prints, like Print Gallery, or his tessellations, often play with concepts of recursion, cyclical space, and infinity. In Print Gallery, a man looks at a picture of a town that contains the very gallery he is standing in, which contains the picture he is looking at, creating an infinite, self-referential loop, a visual representation of a logical paradox. His tessellations, where shapes like birds or fish fit together perfectly to tile a plane, often have their figures shrink towards the edge of a circle, implying an infinite number of ever smaller figures packed towards a boundary, a beautiful visualization of infinity within a finite disk, known as a Poincaré disk model of hyperbolic geometry. These artworks are not just clever illusions, they are rigorous visual explorations of mind-bending math concepts, allowing our perceptual system to grapple with ideas that language alone struggles to convey. Beyond art, thought experiments provide the narrative stage for visualizing the infinite. Return to the image of Hilbert's infinite hotel. Visualize the endless corridor stretching beyond sight. See the manager's calm instruction, the gentle, coordinated shuffle of an infinite number of guests moving from room N to room N+1, creating a single vacancy at the beginning. This is a story, a mental movie, that allows us to conceptualize the counterintuitive arithmetic of countable infinity. The story makes the abstract logic tangible. Now picture the infinite bus arriving. Visualize the guests moving from room N to room 2N, like a perfectly synchronized dance, opening up an entire infinity of odd-numbered rooms. These thought experiments are not just proofs, they are acts of imagination, tools for building intuition about a realm where our normal intuition fails. Consider the infinite monkey theorem. The image it evokes, a chaotic, endless sea of monkeys and typewriters, is absurd, yet it provides a powerful, visceral way to grasp the statistical power of immense numbers. Visualizing this scenario helps us internalize the concept that with enough random trials, any finite pattern is bound to emerge. The thought experiment transforms a dry probability calculation into a vivid, memorable, and thought-provoking narrative about the relationship between chaos and order. Even contemplating the physical infinity of the cosmos is an act of visualization. Stare into the deep blackness behind your eyelids and imagine it expanding outwards forever. Imagine floating through an endless sea of galaxies, knowing that no matter how far you travel, there is always more space, more galaxies stretching on without end. This imaginative act brings the abstract concept of an infinite universe into the realm of subjective experience, evoking feelings of awe, smallness, and wonder. It allows us to feel the implications of the concept, not just understand it logically. The act of visualizing infinity is itself a paradoxical endeavor. We use our finite minds, our finite imagination, to try and represent the limitless. We will always fail to capture it completely. The zoom into a fractal must eventually stop in our mind's eye. The corridor of Hilbert's hotel fades into an indistinct, and so on. But the attempt is what matters. The practice of stretching our imagination to its limits, of trying to picture these mind-bending concepts, expands our cognitive horizons. It is a form of mental yoga, pushing our intuition into new and uncomfortable positions, thereby increasing its flexibility. It connects the abstract world of mathematics and logic with the aesthetic and contemplative faculties of the mind. As you reach the final moments before sleep, engage in this one last act of quiet contemplation. Choose one of these images: the endless zoom into a fractal, the shifting guests in the infinite hotel, the monkey randomly typing a perfect sonnet, the cosmos stretching on forever. Don't try to analyze it further. Simply visualize it. Let the image unfold in your mind. Let it be your final thought experiment of the night, a gentle, wondrous confrontation with the limitless. Find deep relaxation in this act of pure imagination, allowing the beauty and mystery of the infinite to be the final, peaceful landscape your mind explores as it drifts into the boundless realm of sleep.